Hi, everybody. Welcome to our second mini course in machine learning. This section is going to be on unsupervised learning.
That sounds fun. Hi, Michael.
Oh, hey, Charles. I didn't even know you were here.
That's because I'm not really there.
Oh. Well, I'm glad to hear your voice regardless.
Good. I'm always happy to hear your voice, Michael. And I'm looking forward to hearing about un-supervised learning.
Well, unsupervised learning is going to be a series of lectures that we do, but today's lecture is on pistisminiawa,
Okay.
which is randomized optimization. I took the letters of optimization and I randomized them.
You're such a nerd. I love it. Okay.
All right, so the plan is to talk about optimization, and in particular to focus on some algorithms that use randomization to be more effective. But let's talk a little bit about optimization for a moment, because that's something that has come up, but we haven't really spent any time on it. So what I'm thinking about when I talk about optimization, I imagine that there's some input space X, which is kind of like in the machine learning setting, and we're also given access to an objective function or fitness function F that maps any of the inputs in the input space to a real number, a score. It's sometimes called the fitness, sometimes called the objective, sometimes called score. It can be any number of things. But in the setting that we're talking about right now, the goal is to find some value x star in the input space such that the fitness value for that x star is equal to or maybe as close as possible to the maximum possible value.
So that's like argmax then, like we were doing with Bayesian learning.
Yeah, exactly, right. So of all the possible x's to choose, we'd like to choose the one that causes the function value to be the highest.
Okay.
Yeah, I wrote it this way, though, because I thought it would probably be helpful if it's like, because we'd be pretty happy with an x star that isn't necessarily the best, but it's like near argmax, right? Something that's close to the best.
Okay.
So this is a really important subproblem. It comes up very often. I was wondering if you could think of examples where that might be a good thing to do, like in
Well,
life,
like in life.
or computation, which is life.
Computation is life, and life is computation. Well, believe it or not, I was actually just talking to someone the other day who works at is a chemical engineer, works at a chemical plant, and he says there's all these parameters they have to tune when they mix their little magical chemicals, and if they do it just right, they end up with something that is exactly the right temperature, comes out just right. If they're wrong at all, if some of their temperature is off a little bit or anything is wrong, then it ends up costing a lot of money and not coming out to be as good as they want it to be. So, factories and chemicals and optimization and parameters.
Factory, chemical. I'm not sure that's a general category of problem, but I guess maybe the one way to think about it is in we'll call it process control. So if you've got a process that you're trying to put together and you have some way of measuring how well it's going, like yield or cost or something like that, then you could imagine optimizing the process itself to try to improve your score.
Okay. Yeah, I think that's what I meant.
Route finding is kind of like this as well, right? So just, find me the best way to get to Georgia.
What about route finding?
Oh, I see what you did there.
Mm-hmm.
So you could think of route finding as being a kind of optimization as well. If you've got a function and you're trying to figure out where it crosses the origin, you might set that up as an optimization problem. You might say, well, of all the different positions I could be in, I want to minimize the distance between the axis and the value at the point where I chose it. Find me the best one, which is going to be right there.
Actually, when you put it like that, how about neural networks?
Nice. So let's get it back to the learning setting. So what do you mean by neural networks?
Well, I mean, everything we've been talking about so far, X, is some kind of stand-in for parameters of something, a process or I don't know, whatever. So if the weights are just parameters of a neural network, then we want to find the X that, I guess, minimizes our error over some training set or upcoming test sets or something.
Yeah, so minimizing the error is a kind of optimization. It's not a max in this case, but if we, I guess, negate it, you want to maximize the negative error, that it's maximized when the error is 0.
Right.
Cool. Is any other learning-related topics that you can think of that have optimization in them?
Well, I would guess anything with parameters, where some parameters are better than others, and you have some way of measuring how good they are, is an optimization problem.
So decision trees?
Sure.
So what's the parameters there?
They're the order of the nodes, the actual nodes. Like, what's the first node?
Yeah, the whole structure of the tree. So it's not a continuous value like a weight, but it is a structure. We could try to optimize over the structure. There's nothing in the way that I set this up here that makes it so that X has to be continuous or anything like that. We just need a way of mapping inputs to scores.
Okay. So all of machine learning, everything we did in the first third of the class is optimization.
There's some optimization in each of the pieces of it. Yeah, exactly. Because often we say, given this training set, find me a classifier that does well on the training set, and that's an optimization problem. All right, so let's, what we'd really like to get to are algorithms for doing optimization, and I think to do that, it's helpful to do a quiz. So here is a little quiz that I put together. I call it Optimize Me. And what I want you to do is here's two different problems. There's two different input spaces, two different functions, and I want you to find the optimal X star or something really close to it if you can't get it exactly right. So the first question, we've got the input space X is the values 1 to 100, and the function that we're trying to optimize is X mod 6 squared mod 7 minus the sine of X.
Holy cow.
Yeah, it is an awesome looking function. Do you want to see it? I might be able to plot it for you.
Sure, I'd love to see plot, because then maybe I'll know how to figure out the answer.
Yeah. Oh, yeah. Well, maybe I should not then. Maybe I should wait until we already have an answer, and then yeah, let's wait. But I'll show you after it. It's crazy. All right. It's beautiful. So okay, good. So and the second problem, we've got X as the set of real numbers, so any possible number in the reals. And the function that we're trying to optimize is negative x to the fourth plus 1000x cubed minus 20x squared plus 4x minus 6. All right, so you understand the questions?
I understand the questions, yes.
Good. Good luck with them. All right, everybody, welcome back. So let's work through these. Charles, what are you thinking for this first one?
I'm thinking I should write a program and just run it through, because that's the easiest thing to do.
So what you're saying is this f function is so kind of wacky that it's hard to imagine actually analyzing it and doing anything with it. But on the other hand, the space of x values is very small.
Right.
Good. So so we can enumerate all the different possible values and just see which one gives the highest output.
Yeah, that's pretty straightforward if I just wrote the code. In fact, it's like one line of code.
So I wrote it for you.
Oh, good.
I'm nice that way.
You are that way. You optimized our time.
I did. So for what it's worth, this is what the function looks like.
I'm not even sure that's a function.
Isn't that beautiful?
It's something. It looks like DNA gone wrong.
Yeah, totally wrong. Like there's just mutations everywhere. Or it's like a bow tie that then tried to tie itself in another dimension. I mean, like you can see there's this sort of interesting up and downness to it, like the sine wave part, but it, like they're interdigitated with each other. It's just crazy.
Interdigitated. That is an awesome word.
It means to put your fingers together. So
so what happens if you plot that but with connecting lines?
Oh, sure.
Wow.
You get something like that.
Wow.
This is a kind of unfriendly function.
Yes, it's not the friendliest function I've ever seen. Although now it looks a bit like an insane bow tie.
Nice. Electric bow tie.
Yeah. It's kind of cool.
So it turns out that there's 2 points that are really, really close to being the top. There's this one at 11, and there's this one, I don't know, a little bit after 80 or so. But the one at 11 is actually the largest.
This function goes to 11.
It does indeed. So I'm going to say 11. I wanted to make a crazy function. That was the first thing that popped into my head. Actually, the second one was a mod 3 at first.
Well, it's an interesting thing, right? Because if you try to reason this out, it would be very difficult to do. I mean, first off, mod isn't very nicely, it's very easy it's not very easy to deal with algebraically, right, in closed form. But you could start reasoning and say, well, the dominating factor is mod 7 in the sense that you're never going to be greater than 6. And of course, the mod 6 is never going to be greater than 5. So the best you can get there is 5. And then you minus the sign, which is going to be some small number. So you can kind of pick all the values that are going to give you something like 5 there. And then whichever one has the smallest sign, that's the one you go for. I wonder if that would get you anywhere close to the right answer. So interesting. that that's not quite true here because 11 mod 6 is, no, 11 mod 6 is 5, right? So, squared is 25. Mod 7 is 4. Is that right?
Anyway,
Okay.
let's do the second one.
Okay.
All right, so it turns out that, again, 11 and 80 are really close, but 11 is slightly larger. And it's just almost 5, but not quite. All right, so for the second problem, now we can't use the same trick of enumerating because our x's constitute the entire space of the reals.
So there's like 200 of them.
More, even.
Hmm.
So we need to do something else, and I think what you were pointing out to me is that because this is a nice polynomial, we can actually use calculus to figure out where the maximum is.
Right. Just take the derivative and set it equal to 0.
So unfortunately, I made that a little harder than probably you'd appreciate. So the derivative would be this, and setting it equal to 0 would give us this equation, which unfortunately is a cubic.
Right.
So it should have 3 solutions, perhaps. And you could just check each of them, but solving the cubic is sort of a pain. I guess I could have been a little bit nicer.
You could have been.
Sorry about that.
It all depends on what you're optimizing.
So how would you go about solving this now?
I would go on Google and I would look up how do you solve cubics.
Sure, that's not a bad idea. Any other things? Because it is nice and smooth, right? So let me actually plot it for you. So here's the function, and I just plotted a subrange of it from -500 to 1,000. You know, you could ask, well, could it be that the maximum is actually someplace outside this range? Do you know how you'd answer that?
No.
So because it's a 4th order polynomial, like think of it like a quadratic. It's got
Right.
that one bump in it. A cubic can have as much as one up bump and one down bump, and a quartic, a 4th degree polynomial, can have an up bump, a down bump, an up bump, and then back down. So we're actually seeing all the activity here. Outside this range, it just plummets negatively. It can't turn around and come back up again. So because we can see the 2 bumps, we're good.
Okay.
And in this case, it looks like the bump that we want is somewhere between 500 and 1,000, somewhere in the 700 kind of zone. And, well, so one thing we could do, because it is really well behaved, we can kind of zoom in on the function in that range. So there we are now zoomed in from between 500 and 1,000. We can see, okay, well, actually, it looks like the peak is maybe between 600 and 800, you think?
I'd say 700 and 800.
Between 700 and 800. All right, let's take a look at that. Ooh, nice and pointy. All right, so
740
how about that?
How about 740 and 760?
So we really are kind of getting into the nitty gritty here. So for the quiz, we accepted anything between 745 and 755. But in fact, we can keep zooming in, and we can use calculus, and we can really hone in on what the tippy top is there. But that's not so important right now. We could also use something called Newton's method. Do you know Newton's method?
I remember it.
Newton's method says, let's guess a position like 755, and use the derivative at that point, which is actually really easy to compute. It doesn't involve solving the cubic. It just involves writing down the cubic and evaluating at that point. We can actually fit what the straight line is here, and we can take steps in the direction of that line. It's a gradient ascent kind of method.
Yeah.
And that'll allow us to hone in as we get closer and closer to the top. The slope is going to flatten out. We're going to take smaller steps, and this process converges to whatever the peak is. I think it's a little bit under 750.
That looks about right.
So in terms of optimization approaches, we actually just looked at a couple different ideas. We just looked at generate and test, this sort of idea of you can just run through all the different values in the input space and see which one gives the maximum. When is that a good idea? When is that not a good idea?
Well, it's probably a really good idea when you have just a small set of things you need to generate and test.
Yeah, it really does require that we have a small input space. And it's also particularly helpful if it's a complex function, right? Because there really isn't any other choice if the function has kind of crazy behavior, like in the mod example that I gave. All right, for things like calculus, like just solving for what the optimum is analytically, when is that a good idea and when is that not such a good idea?
Well, it's a good idea when you have a function where you can do that. Well, first off, it has to have a derivative.
Right, and so it seems like, well, how are you going to write down a function that doesn't have a derivative? Well, if the thing that we're trying to optimize is some kind of, it could be crazy because we defined it to be crazy. We can define it with little, like ifs and things like that to make it only piecewise continuous. Or it might be that the thing we're optimizing is some process in the real world that we just don't have a functional representation of. All we can do is evaluate the fitness value at different inputs.
Right, or if the inputs are discrete.
Right, like in the first example, right. So it might not actually give us any feedback. The derivative is we're not moving in a smooth, continuous space.
Right. Hey, does mod have a derivative?
Almost everywhere.
Just not everywhere.
Yeah, there's that, because mod kind of looks like, so it has this nice derivative everywhere except for at the jumps.
Which happen pretty often.
Yeah, there's a lot of them, but they're, measure 0.
Okay.
Like if you just picked a random number, it wouldn't be at the jump. So it's not only important that the function has a derivative, but the derivative, we need to be able to solve that derivative equal to 0. Newton's method can be helpful even outside of that case, where we have a derivative, and we have time to kind of iteratively improve, right? Just keep querying the function, creeping up on what the optimum turns out to be. So, okay, but then what do we do if these assumptions don't hold? So we have what would that mean? It would mean, what, big input space?
Still have a complex function.
Complex function.
No derivative or difficult to find derivative.
I knew I had that derivative around here someplace.
It's always the last place you find it.
Indeed. Yeah, exactly. And actually, I should have mentioned one more thing about Newton's method, which is that the function has a derivative, you iteratively improve, and it really wants you to have just a single optimum, because even Newton's method can get stuck if it's in a situation where you have a curve, say, like that, because Newton's method is just going to hone in on the local peak.
So that would be bad if you have lots of local maxima in this case, or optima,
right.
I suppose.
Yeah. So so that's, we can kind of list this as well. Possibly many local optima, right? That the function has a kind of a peak, that things around the peak are less than the peak, but that peak itself may be less than some other peak somewhere else in the space.
Makes sense.
So, as you might expect, that our answer to this hard question is going to be randomized optimization, the topic of today's lecture. So here's an algorithm that you'd probably either already know about or would be able to come up with rather quickly, which is the idea of hill climbing. So if this is the function that we're trying to find the maximum of, then one thing we could do is imagine just guessing some x, I don't know, say this one, which has some particular f of x value, and then to say, okay, well, let's move around in a neighborhood around that point and see where we can go that would actually improve the function value. So here the neighborhood might be, a little to the left, a little bit to the right on the x-axis. And what we find is that in one direction it's going down and the other direction it's going up. So what hill climbing says is find the neighbor that has the largest function value. This is steepest ascent hill climbing. And if that neighbor is above where we are now, has a higher function value than we are now, then move to that point. Otherwise, we stop because we're at a local optimum. So what this is going to do is it's going to iterate, moving up and up and up and up this curve, always in a better and better and better direction, until it hits this peak here. Then it's going to look on both sides of it. The neighborhood, everything in the neighborhood is worse, so it just stops there, and this is the x that it returns. Which is, not a bad answer. It's not the best answer, but it's a good answer.
What if you had started out just a little bit more to the left? Say on the other side of that valley.
Oh, like here?
Yeah.
So then, well, let's see. What would it do? If we start there, we take a step. We say, what's the neighborhood? The neighborhood are the points just a little bit to the left and just a little bit to the right. One of them is an improvement, so it takes the improvement. And again, it keeps finding it more and more improved, and then it gets to this top of this little bump, and it says, okay, both the points in my neighborhood are worse than where I am now. Hooray, I'm done. So that's not even the worst of the local optima. It could actually get stuck here as well, which is even lower.
Well, it could get stuck anywhere. Well, at any peak.
Yes, exactly right, and that's the lowest of the peaks. All right, I want you to guess my word using this hill climbing approach that we've just been talking about. And unfortunately, well, we tried this with actual words, and the space is a little bit big and frustrating. But what we can do instead is pretend that a 5-bit sequence is a word. So I'm thinking of a word, and by word I mean 5 bits. And what we're going to do is I'm going to give you, for each time you guess a 5-bit sequence, I'm going to tell you the number of correct bits. So in each position, it's if you matched what I am thinking of in that position, then I give you an additional point for that.
Okay.
And you're going to now step through the hill climbing algorithm.
Okay. So 3 things. 1, if you had done 8 bits, that would be a word. And
Oh, nice.
2, 4 bits is a nibble. Okay, here's the third thing. We need to define a neighbor function. So I'm going to define a neighbor function so that I can think about this is all 1-bit differences from where you are.
That's good. And an interesting question is, was it your job to come up with that, or was it my job to come up with that? Now, is it part of the problem, or is it part of the algorithm that's trying to solve the problem?
I'm going to say it's a part of the algorithm that's trying to solve the problem.
That's how I think of it too.
All right, so we have to start somewhere. So let's just pretend for the sake of argument we started at all 5 zeros.
And I'm going to give you a score of 2 for that.
Okay, and so now I have to do all possible neighbors, and there are 5 of them. So there is 1 followed by 4 zeros, 0, 1 followed by 3 zeros, and, the rest of the identity matrix.
All right, here's all your neighbors for the X where you were,
Mm-hmm.
and here's the scores for all of those neighbors.
So there are 3 of them that are maximal, but for the sake of simplicity in drawing, I'm going to stick with the first one. So you can get rid of the bottom 4.
All right, so here's our new X.
Okay. And now I have to try all differences. So one of the neighbors would be all zeros, but I already know what that is, so I don't have to worry about that.
That's good. So the algorithm, the pseudocode that we wrote didn't do that optimization, but in general, that as long as the neighborhood function is symmetric, then you can save yourself a little bit of effort.
Right. So or we could just keep track of everything we've ever seen, although that gets very space inefficient very quickly. Since it's the identity matrix concatenated, prepended with the 1 matrix. Okay, so what are the numbers for that one? Wow, that's pretty cool. So it looks like we're getting there very quickly. So it's going to be, so the best.
In fact, do we now have enough information that a smart human being could actually jump to the optimum?
Yeah, I think we do. I was actually thinking about that.
Let's see what happens. All right, let's figure it out.
Well, so first off, I think the first thing, if I'm right, is the following statement true? Once we know 4 of them are right, we will stumble onto the right answer when we do the neighborhood?
Well, so that's a good idea. So we could actually do one more step and see what happens. So yeah, because in this particular case, because of the fitness function is the way that it is, the number of correct bits, there's always a neighbor that is 1 step closer to the target. So we're always going to be incrementing as we go. So this is a very friendly fitness function. It's only a global optimum.
Right. So do you want to do that? And then maybe we could talk about how we could have been even more clever. So let's just pick the first one. Okay. And so now we have to do the fourth one. So it's 1, 0, 1, 1, 0. And then the fifth one is 1, 0, 1, 0, 1.
Good. All right. So if this is X and these are the neighbors of X, these are the scores. And it turns out that one of them actually has all 5 matches. So that was, in fact, the pattern I was thinking of. Here, just to prove it. 1, 0, 1, 1, 0. And if we now continue the search from here, all the neighbors are going to be worse, obviously.
Right.
So how could we have figured out the sequence without that extra information that I just gave you?
Well, if we look at the 2 that have 4, we can basically just see that where they must have 3 in common, which they do. One, the first, the second, and the last one.
Okay.
And each is off by exactly 1. So that means that, well, since I know the answer, I know that you just take one. You just take 1 from each. So either they both have to be 1s or they both have to be 0s.
All right. And so do we know that the 0 one doesn't work?
We probably know that the 0 one doesn't work.
Because then the answer would be 1, 0, 0, 0, 0. 1, 0, 0, 0, 0, which is exactly, we already know is a 3.
Right. So then it has to be 1, 0, 1, 1, 0, which in fact it is.
Which it was. Cool.
Right. So this was in fact a very nice fitness function. And you know, it seems to me that we had a nice little advantage here in that we really understood the structure of our space. But if this were a 5,000-bit sequence where the fitness function was some weird thing, where in fact we didn't even know what it was, we just knew that there was one, then that would have been a whole lot harder. Actually, here's a question for you, Michael. If I had given you this, but I didn't tell you what the fitness function was, just that when you gave me a sequence, I evaluated it for you, we wouldn't have been able to do any of the stuff that we were doing. I mean, we'd still be able to do it, but we wouldn't have been able to jump ahead like we could have done with those two that were 4, because we wouldn't even know what the maximum fitness value was.
Yeah, we would have had to have done this last step to find that one of them has a score of 5, and then we would have had to have done that step again to make sure that there wasn't anything locally better than 5, because we wouldn't have known that if we didn't have a kind of semantic understanding of the fitness function. But the rest of the algorithm was perfectly implementable without knowing that, right? All that you were basing your decisions on was you gave me bit sequences, I gave you scores, and you used those to figure out what next bit sequence to ask. It didn't use the fact that the fitness function had a particular form.
That's right. That's right.
Now, in this one, this particular problem is very, very well behaved because it has one global optimum, this bit sequence that has a score of 5. Nothing else had a 5. And once you're at and no other bit sequence actually could you be stuck, right? So it was always the case that you could always get closer to the target pattern, so your score can always go up. But in general, that's not how things work, that you may actually be able to get stuck in local optima, and we need a way of dealing with that. So random restart hill climbing is going to give us a way to deal with the fact that hill climbing can get stuck, and the place where it gets stuck might not actually be the best place to be. And so we can go back to that function that we looked at before. So what are some places that this can get stuck?
There, and there.
And others to boot. So what randomized hill climb is going to do is once a local optimum is reached, we're just going to start the whole thing again from some other randomly chosen X. It's like, sort of what you do if you were trying to solve a problem and you got stuck. You're like, okay, let me just try to solve it again. So why is this a good idea?
Well, one, it takes away the luck factor of I happen to pick a good starting place. Although I suppose it replaces it with the luck factor that I randomly happen to pick a good place. But that's okay because I'm going to keep randomly picking good places or randomly picking starting places.
Yeah, so you get multiple tries to find a good starting place, that there could be various places where you start that don't do so well, but as long as there's places where you do well, then you might luck into to starting in one of those places and climb up to the tippy top and win.
Another advantage is that it's actually not much more expensive. So whatever the cost is of climbing up a hill, all you've done is multiply it by, a constant factor, which is how many times you're willing to do a random restart.
Yeah, that's a good way of thinking about it, that it's really just random hill climbing repeated however many times you feel like you have time to repeat it. And it can actually do much, much better. Now, if there really is only one if there is only one global optimum and there's no local optimum, then what's going to happen when we do random restart hill climbing?
We'll just keep getting the same answer.
Yeah. Over and over again. So it could be that we might keep track of that and notice, okay, you know what, we seem to be in a space where these random restarts aren't getting us any new information, so we might as well stop now.
Well, that's one answer, but I could think of another answer.
What's that?
So maybe you just keep starting too close to the same place you're starting before. I mean, it may be random, but you can get unlucky in random, right? So maybe you should make certain your next random point is far away from where you started so that you cover the space. You want to cover the space as best you can.
Yeah, the randomness should do that, at least on average. But you're right. So we could try to be more systematic. So here might be an example of a kind of function where that'd be really relevant. So imagine here's our input space, and most of the random points that we choose are all going to lead us to the top of this hill. But a very small percentage are actually going to lead us to the top of the real hill, the top that we really want, the optimum. So yeah, we might not want to give up after a relatively small number of tries, because it could be that there's just this tiny little, I don't know, I'm going to call it a basin of attraction.
Mm-hmm. I like that.
And if it's small enough, it might take lots of tries to hit it. In fact, it could be a needle in a haystack, in which case there's only one place that you can start that has that optimum, and that could take a very, very long time to luck into. In fact, the hill climbing part isn't doing anything for you at that point.
Yeah, but if you're in a world where there's only one point that's maximum or there's only one way to get to it by happening to land on a single point, then you're in a bad world anyway. Right? I mean, there's nothing is going to work out. Nothing's going to help you in that world.
Yeah.
Right. And in fact, I would claim, since everything has some kind of inductive bias, right? You're making some assumption about like local smoothness or something that makes sense here, because if you are worried about a world where there is always some point of the infinite number of points you could be looking at, say, that is the right one, and there's no way of finding it other than having to have stumbled on it from the beginning, then you can't make any assumptions about anything. You might as well just look at every single point. And what's the point of that?
Fair enough.
Mm-hmm.
So the assumption here, I guess, is that you can make local improvements, and that local improvements add up to global improvements.
Right. Hey, I got a question. I got a semantic question for you, a definition question for you.
Sure.
You decided that you didn't, if you only have one optimum, you didn't want to call it a local optimum. So is a local optimum by definition not a global optimum?
So if I was being mathematical about it, I would define local optimum in a way that would include the global optimum. But it's just awkward to talk about it that way because it feels like a local optimum is someplace you don't want to be, and the global optimum is someplace you do want to be. But yeah, that's right. The global optimum is a local optimum in the sense that you can't improve it using local steps.
Okay.
I think we can kind of get at some of these issues with a randomized hill climbing quiz. So what is the advantage of doing hill climbing, and what does it lead to in terms of being able to find the maximum? Yeah, Charles, this is going to be a quiz, and I guess you're not particularly happy about it. But let's take a look here. We've got an input space of 1 to 28, the integers, and so here it is, kind of out on the screen, all the values from 1 to 28, and here's the fitness function or the objective function for each of those points. It sort of follows this, not exactly sawtooth, kind of piecewise, jaggy. I don't know what to call it.
Drunk.
It is what it is. And here's the global optimum. And what we're going to do is we're going to run randomized hill climbing, and we're going to run it this way. We're going to assume that the algorithm chooses randomly in if both directions improve. So it just flips a coin 50-50. Then it does whatever evaluations it needs to do to figure out which way to move to go uphill. We'll use as the neighborhood of x to be the thing immediately to its left and immediately to its right, unless, of course, you're at 1 or 28, in which case there's just one neighbor. So we're just going to use a simplification of the hill climbing that we had before, which is it's going to check the neighbors, check both the neighbors if there's two of them. And if one of them is an improvement, it's going to go in that direction. If neither of them improvement, then it's going to declare itself at a local optimum. And if both are an improvement, it's just going to flip a coin to decide where to go. And once it gets to the local optimum, let's say it sort of climbs up this hill and ends up at this peak here, it's going to realize that it's at a local optimum, and then it's going to trigger a random restart and pick a new x position to start at. And now the question is, how many function evaluations on average is it going to take to find x star, the tippy top of this peak? So, maybe you could write code to do this, or maybe you could do it with math. This is probably a little bit more involved than most of our quizzes, but it should give you a chance to really dive in and get a feel for this notion that it matters kind of where these basins of attraction are. All right, do you think that's clear enough to give it a shot?
Sure.
All right, let's go. All right, so there's a bunch of ways you could imagine doing this, and here's how I would suggest looking at it. So for each of these 28 positions, there's some number of steps that it's going to take before it either resets, that is to say, re-chooses at random, or has actually reached the tippy top. So let's actually evaluate these. So if you happen to start at 1, how many steps is it before you realize that you're at 1? You have to evaluate 1, you have to evaluate 2, you have to evaluate 3, and you have to evaluate 4 to see that you're a local optimum.
Mm-hmm.
So there's going to be 4 evaluations if you start at 1. If you start at 2, then it's going to be 1. You're going to have to evaluate 1, 2, 3, and 4 again. If you start at 3, then you only need to evaluate 2, 3, and 4 to know that you're at a local optimum.
Mm-hmm.
If you start at 4, then you'll have to evaluate 4, and then if you randomly step in this direction, you're also going to need to evaluate 2, 2, and 3. All right, so then I've finished writing down what all these different numbers are. For each position here, I wrote down in red how many steps it's going to take before it hits a local optimum, including the ones here around the actual peak. And I wrote 2 numbers for the places that were these cusps where it can go either way. So now we can actually work out what the expected number of steps to the global optimum is. It turns out for 22 out of 28 of these points, they average 5.39 before they discover they're actually at a local optimum, at which point we have to start the whole process over again. And so whatever the expected value of reaching the local optimum is, we incur that same cost again.
That makes sense.
Good. Okay, so for 4 out of 28, these guys here, then they're going to take 4 steps on average and end up at the peak. Then the only other things that left to figure out are what happens at these 2 weird cusps where it's going to flip a coin and either get stuck at a local optimum that's not global or go to the global optimum. So in 2 out of 56 of these cases, it's going to have chosen to go to the local optimum, the non-global local optimum, and it just so turns out that it's 10 in both of those cases. It's 10 steps before you realize you're stuck again, at which point it's going to start the whole process over again because it's stuck. Then in 1/56 of the cases, we're going to be here and choose to go to the right and take 6 steps to get to the global. And here, 1/56 of the cases, we're going to take 5 steps and get to the global.
Okay, so just to be clear, so the way you got 28 is that there were 28 numbers and you uniformly chose where to start.
Yep.
Where you got 56 is you decided that for 2 of those numbers, 15 and 20, you end up getting them 1/28 of the time, and then half the time you do the local optimum, and half the time you end up doing the global optimum. And it just turns out that in the cases where you end up going to the local optimum, those both happen to take 10 steps, and that's how you got 2 out of 56. And the last thing to notice is that for point number 4, where you could go to the left or to the right, since you do each half the time, it's like saying the number of steps there is just 11/2.
On average, yeah, very good. Yeah, so that was folded into this 5.39 number. You're right. Thanks for pointing that out.
Okay, sure. So this all makes sense. And obviously, if you just add those all up, you can solve for V, and the answer is exactly.
So just algebraically simplifying this equation gives us V equals 5.36 plus 0.82V. Solving for V gets us 29.78. So it only takes 29.78 function evaluations before we first hit the maximum. Ta-da.
Michael?
Yes, sir.
So that seems unfortunate because here's a really simple algorithm. For I equals, or hey, let's say X. For X equals 1 to 28, compute F of X. If it's bigger than my previous one, then hold on to it and then just return whatever is the biggest number I see. So that's linear, and that's 28 evaluations, which is less than 29.78.
Yeah, that's a good algorithm in this case. But I guess your point is that this whole idea of hill climbing and using this local information is actually costing us a little bit compared to just enumerating all the possible inputs and just testing them all.
Right, which I guess makes sense because the numbers are really small, and you have a whole bunch of local optima, and so it's going to take you a long time to luck into the right one. But it seems kind of sad that there's nothing clever you can do here to do better than 28, which is kind of what you want to do.
Well, there's a couple clever things we could do, right? So one is we could random restart faster. It turns out, so here's a question. What happens if you randomly restart after each function evaluation? How many function evaluations do we have to do on average before we reach the maximum?
I don't know. Oh, well, I guess it would be less than 28.
It would be exactly 28.
Oh, it would? Well,
Yeah.
28's less than 28, so that's fair.
It's less than or equal to it, sure.
Yeah, that's what I meant.
And even better, what happens if we actually keep track of points that we visited in the past?
Oh, then we don't pay the cost for reevaluating them.
That's right.
So then the only question is, how long does it take us to luck up into getting between 15 and 20?
Yes. Well, once we fall into that zone, then we're going to be done shortly afterwards.
Right. So how much of a win is that on average?
That's a good question. It's a little bit hard to tell because what's going to happen is if we follow this algorithm with the additional additional attribute that says if you already know the function evaluation from some previous iteration, we just reuse it. We don't pay the cost for that. Then what's going to happen is we're going to get dropped off in random places in this space. We're going to hill climb, visiting some things along the way, and possibly get dropped someplace where we've already done the function evaluation.
Right.
And therefore don't have to pay that cost again. But it's not as simple as just saying how many different hops do we take before we land in this basin, because if we land in, say, this basin here, the second one from the left, if we get dropped onto point 14, it's going to stay in that zone for a while, which is actually kind of bad because it's taking lots of function evaluations in that same part of the space.
But what you just said is important, right? Since we're only going to pay the cost of doing a function evaluation once, that means in the worst case, we would end up hitting the 3 bad basins before we hit the 4th basin. And in fact, we would end up hitting the 3 bad basins enough times that we would end up visiting all of the points in them. So we'd land in point 14, which would get us all the way over to the peak and just to the left, and then we would land in point 5, which would get us to the right. So we cover everything in the basin. So the worst case is we cover every single point in all 3 of those basins before we get lucky enough to land in the good basin.
Right.
And then, but the moment we land in the good basin, we will get to, am I right? We will get to avoid at least one of those numbers.
No, not necessarily. So, for example, if we start at 15 and we randomly move to the right, to know that we're at the optimum here, we have to check the point 19. So we've actually touched everything.
No, we didn't touch 20.
Well, we might have already unluckily hit 20 because it's part of the right-hand basin as well.
That's
well,
true.
anyway, the point is that you're right. If we keep track of which points we've already visited, then we can't do worse than 28. Like, even if we're really, really unlucky, we can't do worse than 28.
Right.
Maybe on average it'll be a little bit better than that. But only 1 or 2.
But it'll still be better.
I think
on
it'll
average.
still be better.
On average,
yeah,
it'll be
it's
better.
true. I think in this case it's just a contrived example with lots of local optima and just a linear space, so that there's the attraction basins end up being relatively small compared to the size of the space.
Okay, that makes sense. So what should I learn from this? So I guess what I learned is randomized optimization or randomized hill climbing here may not do better than evaluating all the space in the worst case, but it won't do any worse. And every once in a while, you will get lucky and do much better, at least if your cost is function evaluations as opposed to steps.
That's right. Yeah, and also, well, and the thing that I was hoping that you'd notice is this idea that randomized hill climbing depends a lot on the size of the attraction basin around the global optimum. So if we make that really big, then this is a huge win. If we make it really small, then it's less of a win.
No, and that makes a lot of sense. Right. So if the third one had gone all the way from, say, number 3 to number 26, then you would fall into it immediately, and you'd get there very quickly.
Right.
Okay, yeah, I see that. That makes a lot of sense. So when you asked me before what the advantages are, you're in a place where the attraction basin for your global optima are in fact relatively big. Once you luck into that part of the space, and there's lots of ways to luck into that part of the space, you can get there very quickly. So it's a big win.
Agreed.
Okay, good. Okay, that makes sense to me. I like that.
All right, we're going to look at another algorithm that kind of takes the idea of random restarts one step further. Instead of just waiting until you hit a local optimum to decide that you're going to randomly restart, there's always a chance of taking a step in a downward direction while you're trying to do your hill climbing. And the algorithm that we're talking about concretely is called simulated annealing. So the basic idea is that we don't always improve. Sometimes we actually need to search. We need to take the point where we are now and wander away from it with the hope of finding something even better. And you can think of this as being related to the notion of exploring and exploiting. That hill climbing, what it's doing is always trying to exploit. It's always trying to climb its way up the hill as quickly as it can, which can lead it to getting stuck. Exploring is the idea of visiting more of the space with the hope that you can actually climb even further.
So which is better then, exploring or exploiting?
Well, you have to trade these off really carefully. So if you're just exploring, it means you're just randomly wandering around the space. You're not using any of the local information to improve yourself. But if you only exploit, then you can get stuck in these local optima. So you need to do a bit of both.
So since I'm always trying to connect this back to stuff we talked before, if you exploit all the time, that's kind of like overfitting, right? It's like believing your data too much and not taking any chances at all. Does that make sense? Or is that too much of a stretch?
It doesn't make sense to me, but I'm sure it makes sense to you.
It makes sense to me.
So you want to think of that as being kind of like overfitting.
Well, if the fundamental problem of overfitting, right, is believing your data too much and dealing with just the coincidences of what you happen to see. That's like being very myopic. And exploiting, in this case, only taking the direction which you go is like believing the data point where you happen to be. I predict from this one example that I should be headed in this direction, and I don't care about anything else, and I'm not going to worry about anything else. Well, that's kind of like believing too much, which is sort of what overfitting is. Meanwhile, search, on the other hand, the exploring is like believing nothing and taking advantage of nothing. So obviously you need to take, as you said, take advantage of the local information. You need to believe it at least a little bit, at least some of the time, or otherwise it's as if you've learned nothing.
All right. Well, I definitely agree with you that there's a trade-off there and that there's a resemblance to overfitting. I don't know how deep that resemblance is.
Superficial. They're like twin cousins.
Twin cousins from another family
Mm-hmm.
branch. So the simulated annealing algorithm that we're talking about is related to an algorithm called Metropolis Hastings, which I always thought sounded really cool. And the whole idea of it actually gets into metallurgy. So here I drew a picture of a sword. And we want the sword, when we're making a sword, if we're a blacksmith and we're making a sword, we want it to be nice and hard. And the way to make it hard and sharp and well structured is for all the molecules to be aligned in the same way so they fit together very snugly and they kind of lock in. And so there is a bit of an optimization process that has to happen. There's all these different ways that the molecules can be arranged, and we would like to settle into an arrangement that has the lowest energy. Well, it turns out that the way that blacksmiths have figured out to do this is they will make the sword and then do repeated heating and cooling. And that actually they can see that that actually strengthens the blade. And what's really happening at the molecular level is it's giving the molecules an opportunity to realign themselves to find an even better solution to the problem of how they can all fit into that space. So this annealing is this idea of heating and cooling. And we're not really literally heating and cooling, though, of course, when we run the computer, it is getting a bit hotter. We're just simulating the idea of the temperature changing. So that's kind of just the motivation for the simulated annealing algorithm, but there's an actual algorithm, and it's remarkably simple and remarkably effective. So the algorithm goes like this. We're just going to repeat for some finite set of iterations. We're going to be at some point x, and we're going to sample a new point, x sub t, from the neighborhood of x. And then what are we going to do? Well, we're going to move our x to that xt probabilistically. So in particular, we've got this probability function px(xt)t, which is going to help us decide whether or not to actually make the move. And the form of that function is written out here. So the probability that if we're currently at x and we're thinking about moving to x sub t, little t, and the current temperature is capital T, then what's going to happen? If the fitness of the new point is bigger than or equal to the old point, we're just going to make the move. All right. So we always hill climb when we are at a point where we can do that.
So that's just regular old hill climbing.
It's kind of like hill climbing, exactly. It's a little different from the hill climbing the way we described it, where we said, let's visit all the points in the neighborhood. This is kind of a useful thing to be able to do when the neighborhood's really large, is just choose anything in the neighborhood, and if it's an improvement, go for it.
Okay.
But what if it's not an improvement? Well, if it's not an improvement, what we're going to do is we're going to look at the fitness difference between the point that we're evaluating and the point where we are now. Look at the difference between those two. Divide that by the temperature. Take e to that and interpret that as a probability. And we either make the move or not with that probability. So, all right, so we got to dive in a little bit to this expression to make some sense out of it. So what happens, Charles, if the point that we currently visited, x, then we visit a neighbor point, xt. What if their fitnesses are really close to each other? Say, just infinitesimally close to each other.
Well, if they're infinitesimally close to one another, then that means that difference is going to be very close to 0.
Right. And so we get 0 over, it doesn't matter what the temperature is, we get 0. E to the 0 is 1, so we make the move if it's infinitesimally smaller than where we were now.
Mm-hmm.
All right. What if it's a big step down?
Well, then that means that number is really, really negative.
Yes.
And then negative divided by some positive number. T is a temperature, so T is always greater than or equal to 0?
Yeah, let's say that.
Okay.
In fact, probably making it equal to 0 could run us into trouble. So let's just say that it's bigger than 0.
So it's Kelvin. So it's in Kelvin. Okay, so that'd be a really, really big negative number, and e to a really big negative number is 1 over e to a really big number, so that makes it very close to 0.
Good. Right. So in other words, if a giant step downward, we probably won't take it.
Right. Okay, that makes sense. So you're sort of smoothly going in directions that kind of look bad as a function of how bad they look, and sort of exaggerating that difference through an exponential function. Right? Okay.
Sure.
So
if that gets you going.
Well, so 3 isn't 3 times worse than 1. It's 2 to the 3 times worse than 1.
I see, or e to the. Well, so good. But let's look at one more thing with this equation here. Let's say that there's a moderate step down.
Mm-hmm.
So it's not so huge that when we divide it by t, it's essentially negative infinity. Let's just say it's a smaller thing, -5 or something like that.
Okay.
Then what happens? Now we get some e to the that is going to be some probability between 0 and 1. What does t do in this case? What if t is something really big? What if t is something really small?
Well, if t is something really big, let's say infinity, then it doesn't matter what the difference is. It's effectively going to be 0.
Right, so a really big temperature here means that we're going to have some negative thing divided by something else. This is going to be essentially 0, and it's going to be e to the 0, so it's going to be 1. So when the temperature is really high, we're actually willing to take downward steps, and we don't even sort of notice that it's going down.
Right.
There's lots of randomness happening.
Right. So in fact, if t is infinity, it's really, 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 really hot. Then even if the neighbor is much, much worse off, he'll be less worse off than infinity. And so basically, you're always just going to jump to the next person, to the next neighbor, to the next point.
Right. So we're very likely to accept. So it's going to move freely. If t is really small, as t approaches 0, what happens?
Well, let's just take the extreme case. So if t was 0 or effectively 0, then that means any difference whatsoever basically becomes infinity.
Right. It gets magnified by this very, very small t.
Right.
And so then it's not going to take any downward steps. It's only going to go uphill. Yeah, so that's kind of the essence of the simulated annealing algorithm. So maybe we can talk about some of its properties.
Okay.
What are some of the properties of simulated annealing? Now, we already talked about 2 of them, this idea that as the temperature goes to 0, it's acting more and more like hill climbing, only taking steps that improve the fitness. And as t goes to infinity, it's like a random walk around the neighborhood. So wherever point where it is, it's willing to go to any of the other points in the neighborhood, and it just doesn't really pay any attention to the fitness function anymore.
So, So that makes sense, right? If I wanted to go with the analogy, high temperatures like a lot of heat, which is a lot of energy, and so molecules bounce around a lot. That kind of has the effect of flattening out the fitness function. T goes to 0, that's no energy. It's like you're frozen, molecules can't move, and so you only move to places with lower energy, or in this case, higher fitness. So that all makes sense. So how do I get from one to the other? You had in the algorithm decrease t, but do we need to decrease t quickly, slowly? What's the right way to do it?
So in practice, we want to decrease the temperature slowly because it gives the system kind of a chance to explore at the current temperature before we start to cool it out. So one way to think about it is if you consider some kind of function that we're trying to optimize, when the temperature is high, it kind of doesn't notice big valleys. It's willing to kind of wander through big valleys. As the temperature gets cooler, the valleys become boundaries and it starts to break things up into different basins of attraction, but smaller gullies it still is able to walk over. As the temperature gets even lower, those become barriers as well. And so what we really want to do is give it a chance to kind of wander to where the high-valued points are before cooling it so much that it can't now bridge the gulf between different local optima.
Okay, that makes sense. So property is it's sort of bouncing between exploration and exploitation. I buy that. So where do you end up?
Well, if we're lucky, we end up at the global optimum. Yay.
Is there anything, we could say? We could characterize how often we end up there? Or are we going to have to do randomized restarts and do simulated annealing a million times?
So we're not going to be able to go through the argument for exactly why this is true, but there is a remarkable fact about simulated annealing that is worth mentioning. That the probability of ending at any given point x in the space is actually e to the fitness of x divided by the temperature and then normalized, because this is a probability distribution over the input space. So this is pretty remarkable, right? So this is saying that it's most likely to be in the places that have high fitness, right? Because those are where it's going to have the highest probability of being. And you can see now what the relationship with the temperature is here too, that as we bring the temperature down, this is going to act more like a max. It's going to put all the probability mass on the actual x star, the optimum. And as the temperature is higher, it's going to smooth things out and it'll be randomly all over the place. So that's why it's really important that we eventually get down to a very low temperature. But if we get there too quickly, then it can be stuck, right? Because it's spending time proportional to the fitness. So it is spending time ending up at points that are not the optimum if they're, say, close to the optimum.
Okay. So, I actually, now that you spell that out, I actually recognize this distribution. It has a name. It's called the Boltzmann distribution.
That's exactly right. And if there's people listening that have a physics background, they're going to probably be poking their eyes out because it's the case that we're using a number of physics concepts, but we don't quite use the same notation and we don't quite do things exactly the way that a physicist would. So there's definitely a relationship. And the Boltzmann distribution is used quite a bit in the physics community, but it may not be exactly like that. So don't try not to panic.
Yeah, it's more like an analogy, like so much of life. It's a simulated Boltzmann distribution.
It's like a simile. All right, there's one more class of randomized optimization algorithms that is really attractive. It's very interesting to people. It has proven itself time and again, and it is this notion of genetic algorithms. So the main insight that's exploited in the genetic algorithm setting is this. So let's imagine we've got a two-dimensional space, and it's hard for me to actually draw a fitness surface over a two-dimensional space. So just kind of think of this as being one of those maps, those contour maps. And so imagine that we've got one dimension, that x now comes in these two different dimensions, and what we're trying to do is find the peak, which happens to be there. So what if we actually evaluate three different points? So these green points here, we actually check what the values are at these points. And what we find is that from this initial point, this green point here, if we increase on dimension 2, we get a better value. But it's also the case that starting from that point, if we increase on dimension 1, we get a better value. So maybe what we ought to do is take kind of elements of these two solutions, these two inputs, and combine them together and move out on dimension 1 and dimension 2, and maybe that will actually give us a good score as well. And in this particular case, it puts us right in the basis of attraction of the local maximum. So this turns out to be useful in many spaces, especially spaces that can be specified combinatorially like this, where there's these separate dimensions that contribute in various ways to the overall fitness value.
Okay, Michael, that sort of makes sense. But what does this have to do with genetics or algorithms for that matter?
Well, it's an algorithm in that it's an optimization algorithm. And the genetic part is because what we're going to do is we're going to build an analogy with biological evolution.
Analogies.
In particular, instead of thinking about these input points, these little green dots, we're going to think of them as each input point is like an individual, and a group of them taken together is like a population. It's really the same idea, but we're just giving it a different name.
Okay.
The idea of local search, where you make little changes to an input, we're going to now call that mutation, right? Where you take an individual and kind of tweak it a little bit,
like we did in the example we did before, where we defined the neighborhood as every one difference in every single bit.
That's right. So the mutations can happen along neighborhoods. It's the same kind of concept as that.
Okay.
And then, and you can see that there's the mutations happening over X, so I assume that you get X-Men.
I think that's a fair point. I like your science.
That's right. It is science. Those are all concepts that we were already using when we were doing these other randomized optimization algorithms. One thing that's different, though, is the notion of crossover. So what crossover does is it takes different points, like this green point and this green point, and instead of moving them just to their own neighborhood, it gives you a way of combining their attributes together with the hope of creating something even better. So that is where it starts to actually kind of deviate from the standard notion of local search or randomized optimization and gets us into something that feels a little bit more like evolution. So this is kind of like, dare I say, sexual reproduction, right? Where the two parents can actually form a new kind of offspring that, if you're lucky, has all the positive attributes of both of the parents, like my children.
And if you're unlucky, it has the worse attributes of the parents, like other people's children.
Exactly. And finally, what we were calling iteration before, in the context of genetic algorithms, we can call it a generation, because we're going to take a population of individuals and kind of, mate them together to create a new population of individuals. And we're going to, what we hope is improve iteration by iteration.
Okay, that makes sense. So if I can just push on this a minute, it seems like if it weren't for crossover, this is really like doing random restart, except instead of doing restarts, you just do them all at once because we have parallel computers.
Yeah, I think that's fair. I think that's quite fair, actually.
Okay, so then the thing that makes it more than that is crossover. that somehow these parallel random searches are bleeding information back and forth. Oh, maybe bleed's the wrong.
Yeah, you don't want to get too biological about this.
Yes, so they're sharing fluids, metaphorically, with one another and conveying information that way, just the way genes do.
Right, and so that's this sort of interesting concept that now we have information not just in the individual, like we're moving that one individual around and trying to find better and better solutions, but the population as a whole represents a distribution over individuals, and that distribution might actually be a useful thing to guide the search for higher scoring individuals.
Okay, that makes sense.
Here's a skeleton of an algorithm that implements a GA. So what we need to do is we start off with some initial population, and usually the population size is fixed to some constant. We'll call it K. So we just generate a bunch of random individuals to get things started. Then what we're going to do is we're going to repeat until essentially things converge. We're going to compute the fitness of all the individuals in the population, and then we're going to select the most fit individuals. So how do you suppose we might decide on which ones are the most fit?
The ones you're most likely to go to the prom with?
Some people choose people differently than just whether they're fit. I guess it depends what you mean by fit. Do you mean like fit like physical fitness?
Well, I meant fit like, well, I did. But I guess fit like whatever the fitness function tells you is fit.
Right. Okay. So since we applied the fitness function F to all the individuals, we have scores for them. And if we want to select the ones that are most fit, which ones do you think those would be? I guess you're saying those would be the ones with the highest scores.
Yeah.
So that's definitely one way to do it, where what happens is you take the, say, top half of the population in terms of their scores, and we declare them to be the most fit and everybody else to be the least fit. But there's other ways you can do it as well. This is sometimes called truncation selection, but there's also an idea called roulette wheel selection, where what you do is you actually select individuals at random, but you give the higher scoring individuals a higher probability of actually being selected. So we don't just strictly choose the best ones. We choose weighted by who's the best.
So does this get us back to exploitation versus exploration then?
I think it does. I think I was certainly having that thought when I was saying it out loud, that it's a similar kind of idea. And in fact, you can use Boltzmann distribution type ideas, simulated annealing type ideas for doing this selection, where you have a temperature parameter. If you set the temperature parameter to 0, then you get something like just choosing the top half. And if you set the temperature to be something like infinity, then you're just going to randomly choose individuals from the population. Irregardless? No.
Irregardless is a word.
Is it really?
Yes, it's actually a word.
Irrespective is what I wanted to say. Irrespective of the fitness of those individuals.
Well, irregardless, I understand what you mean.
All right, so then we declare some of them as the most fit. Then what we're going to do is pair up those most fit individuals. This is like a dating service now. And let them produce offspring using crossover. And maybe a little bit of mutation too. So instead of just taking the combination of the two parent individuals, we take their combination and then we make little local changes to it to mutate them. And we let the value of that pair, that new offspring, replace one of the least fit individuals in the population.
So, Michael, can I ask you a question?
Sure.
So I'm having a hard time figuring out what crossover means. Can you draw me a little picture?
Sure. Though this might be rated R.
That's fine.
No, you're right, because we're going to do it. Well, so it turns out that this is sort of generic. We can define crossover in many different ways, but I think you're right. I think it's worth looking at some concrete examples because it gives you some insight into why this operation might be useful.
Okay.
So let's do a concrete example of crossover. And so it turns out that the crossover operation is always going to depend critically on how you represent the input space. So let's say concretely that our input space is 8-bit strings. So here's two parents, 0110, 1100, and 110, 111, and we're going to introduce them to each other. All right, now they know each other.
Mm-hmm.
And now we're going to use them to create a new individual, a new offspring.
So they're really going to know each other.
All right, now we've put these two bit sequences together, and we've lined up so that the bits correspond in each of the different positions. And now we can ask, how can we use this to generate a new individual that uses elements of the two individuals that we had? So can you think of any ways to do that? Yeah, okay, what do you got?
I have lots of ways, but I don't think any of them can be reproduced for the purposes of this learning lesson.
All right, well, so let's do ones that really kind of stick to the bit patterns.
I swear, there's no way you can say this without getting in trouble, Michael.
All right.
but that's okay. So how about here's an obvious one, right? If we really push the genetic notion as far as we can, then each of those things represent, I don't know, alleles or some other biological term, and so what happens in genetics, right, is you mix and match your chromosomes and your alleles together. So why don't I say one child is the first 4 bits of this handsome Charles fellow, and the last 4 bits of this beautiful and wonderful Sheila person.
All right, I see what you're doing there. So what you're saying is we're going to pick, well, maybe this isn't quite what you said, but I'm imagining that what you said is we pick a random position along the sequence, and you said at the halfway point, and what we're going to do is now mix and match and create 2 offspring. One uses the first half of Charles and the second half of Sheila, and then the other one is the other way around. And as you can see, it's this last bit that determines the sex. Anyway, so these are the 2 offspring that these 2 individuals have generated. And this particular way of combining, where you randomly choose a position and then flip-flop, is called one-point crossover. All right, so now I want you to think about this for a second, Charles. So I don't know if it's an inductive bias, but what kind of bias do we put in when we say, well, we're going to choose one of these points and we're going to flip-flop based on where that point is chosen? Like, what is that going to? What kind of offspring is that going to generate?
Huh. Oh, so you know what? I see two kind of assumptions built there. So maybe that is an inductive bias. So, or a bias of some sort. So one assumption is that locality of the bits matter.
Good.
Right. So the first, by picking halfway through, you're saying the first 4 bits are somehow related, and the last 4 bits are somehow related, because otherwise it wouldn't make any sense to talk about them being together. And that brings me to my second point, which I guess really is just the first point, which is that it assumes that there are subparts of the space that can be kind of independently optimized that you can then put together. Right, and in particular, when I say subspaces to optimize, I mean that they're independent part of the subspaces. So that's actually the example that you gave before. You said, well, there's these 2 dimensions, and each dimension kind of matters independently, and the total reward or the total fitness is some kind of linear combination of them. And so I can put them, because if those 2 things aren't true, then really doing crossover like this won't help you at all. You're just kind of randomly mixing things together.
It's kind of an assumption about the way the space works, in that, kind of like the example we did when we were doing bit guessing, that that you can be heading in a good direction, that there's pieces that are right, and if we reuse those pieces, we can get even righter.
Sure.
All right, so, and if it is the case that the sequence of the ordering of the bits matters, we have this locality property, this is actually a fairly sensible thing to do. But can you imagine any other way of combining these bits together to get offspring?
Well, I can think of a lot.
Well, so let's focus, you have many different possible ideas, but let's focus on ideas where we still have this subspace to optimize property, but we don't really have a locality of bits property, that we don't really, the ordering doesn't matter anymore. So keeping them clumped together like that, we don't think that that's a useful thing.
Okay, well, what would that mean? Tell me what that means.
Well, so the one-point crossover, when we talked about that, it really matters that the 2 bits that are next to each other are very likely to stay connected, right? That it's unlikely that the split will happen exactly between them, and so they'll tend to travel as a group. But if we don't think it's important that the bits that are next to each other need to travel together, if we say that it should be equally likely for any of the bits to kind of remain together, we need to cross over a lot more than just that one time. And in a sense, we might need to cross over every time. Well, so what I'm trying to get at here is this notion that what we could do is we can generate individuals by just scrambling at each bit position. Okay. So the first bit position, maybe it stays the same. The second one flips. The third one stays the same. The fourth one stays the same. The fifth one flips. The sixth one stays the same. Seventh one flips. And the eighth one stays the same. So now we've got 2 individuals, and every bit from these individuals comes from one of the parents. And so that means that if there's little subpieces that are correct, that may be preserved in the offspring. But no longer does it matter what the ordering is. We get exactly the same distribution over offspring no matter how we order the bits.
Okay.
So this idea is sometimes called uniform crossover, and essentially we're just randomizing at each bit position. this kind of crossover happens biologically at the level of genes, right? So we imagine that we get our genes from our parents, but for each different gene, like the gene for eyes and the gene for hair color, are not particularly linked to each other, that they're uniformly chosen at each position. So that's really all I wanted to say about genetic algorithms. I mean, there's lots of tweaky things that you need to do to get this to work very effectively. You have some choice about how to represent the inputs, and you have some choice about how you can do your selection and defining your fitness function. But at a generic level, it's a useful thing. Some people call genetic algorithms the second best solution to any given problem. So it's a good thing to have in your toolbox. But I think that's really it. That's all I wanted to say about randomized optimization. So what have we learned?
Well, we learned about randomized optimization, period, that there is a notion of optimization in the first place.
So we talked about optimization in general, and then what was the randomized part?
Well, we take random steps, or we start off in random places, or we do random well, actually, really, that's really it. You take random steps, you start off in random places, and it's a way to overcome when you can't take a natural gradient step.
That's right. So we talked about some particular randomized optimization algorithms.
Let's see, it was randomized hill climbing.
And we had two flavors of that.
Right. We did simulated annealing, and we did genetic algorithms.
And don't forget that we talked a little bit about how this all connects back up with learning, because in many cases we're searching some parameter space to find a good classifier, a good regression function. Later in this particular subunit, we're going to be talking about finding good clusterings. And so this notion of finding something that's good, finding a way to be optimal, is pervasive throughout machine learning.
Well, that makes sense. Well, if we're trying to remember all these other things we learned, we also learned that AI researchers like analogies. Both simulated annealing and generic algorithms are analogies. And they don't just like analogies, they like taking analogies and pushing them until they break.
Indeed, actually, hill climbing is an analogy too.
Yeah, actually, right. Every single thing that we did is an analogy to something. Okay, that's good. The other thing that we learned, which I think is important, is that there's no way to talk about crossover without getting a bunch of people in the studio to giggle.
Yeah, genetic algorithms make people blush.
Okay, that's pretty good. But Michael, you know, I'm looking at all this, and now that you put all these words together on one slide, I have two observations I want to make that are kind of bothering me. So one is, I'm looking at hill climbing. That makes sense. Hill climbing restarts makes sense. Annealing makes sense. But you know what? They don't really remember a lot. So what do I mean by that? So you do all this hill climbing, and you go 8 billion steps, and then what happens? You end up with a point. You do simulated annealing. You do all this fancy stuff with slowly changing your temperature and creating swords with blacksmiths and all that other stuff you talked about. And in the end, at every step, the only thing you remember is where you are, or maybe where you last were. And with genetic algorithms, it's a little more complicated than that because you keep a population, but really you're just keeping track of where you are, not where you've been. So in some sense, the only difference between the 1 millionth iteration and the first iteration is that you might be at a better point. And it just feels like if you're going to go through all this trouble of going through what is some complicated space that hopefully has some structure, there should be some way to communicate information about that structure as you go along. And that sort of bothers me. So that's one thing. The second thing is what I really liked about simulated annealing, other than the analogy and hearing you talk about strong swords, is that it came out at the end with a really nice result, which is this Boltzmann distribution, that there's some probability distribution that we can understand that is actually trying to model. So here are my questions then. It's a long way of asking a real simple question. Is there something out there or something we can say more about not just keeping track of points, but keeping track of structure and information? And is there some way that we can take advantage of the fact that all of these things are somehow tracking probability distributions just by their very nature of being randomized?
That's outstanding. Yes, very good questions. It is true that these are all kind of amnesic, right? They kind of just wander around and forget everything about what they learned. They don't really learn about the optimization space itself and use that information to be more effective. There are some other algorithms that these are the kind of the simplest algorithms, but you can recombine these ideas, sort of crossover style, to get other more powerful algorithms. There's one that's called taboo search that specifically tries to remember where you've been, and you're supposed to avoid it, right? These become taboo regions. to stay with the idea that you should stay away from regions where you've already done a lot of evaluation, so you cover the space better. And then there's other methods that have been popular for a while that are gaining in popularity, where they explicitly model the probability distribution over where good solutions might be. So it might be worth actually talking a little bit more about that.
Okay, so go ahead.
Well, so I kind of out of time. Maybe you could look into this. I can give you some references, and maybe you can report back.
Fine.
You'll learn very well by doing that.
Yes, sir.
All right, we'll see you then.
Okay, I'll see you then too. Bye, Michael.
Bye, Charles. Here's what I'd like to do. You pointed out some issues that you were concerned about, and I thought that maybe you could go and look into it a bit more, and you did. And so why don't I turn things over to you so that you can tell us what you found out.
Okay, well, thank you, Michael. Hi again.
Hi.
Thank you, Michael. So I did go and I started trying to deal with these issues. So just to recap a little bit, there were two problems that I had, more or less, and they were that we had all these cool little randomized optimization algorithms, and most of them seem to share this property that the only thing that really happened over time is you started out with some point and you ended up with some point, which was supposed to be, the optimal point. And the only difference between the first point and the last point that you did, or the 1 millionth point, or however many iterations you have, is that that point might have been closer to the optimum by some measure. And very little structure was actually being kept around or communicated. Only the point was being communicated. Now, you could argue that that isn't quite true with genetic algorithms, but really you move from a single point to just a few points. The other problem that I had is that we had all of this sort of probability theory that was underneath what we were doing, all this randomization. But somehow it wasn't at all clear in most of the cases exactly what probability distribution we were dealing with. Now, one thing I really liked about simulated annealing is that you were very clear about what the probability distribution was. So what I decided to do is to go out there in the world and see if I could find maybe a class of algorithms that took care of these 2 points for us. And I found something. You'll be very happy to hear, Michael.
Yeah, I would love to find out what it is.
It turns out that I wrote a paper about this almost 20 years ago.
How did you find that?
I just said, well, if I wanted to start looking someplace, I should look at home first, and I stumbled across this paper that I wrote.
I see. So learning about machine learning really begins at home.
That's exactly right. So I had to reread the paper because, it is a couple of decades old. And I will point out that a lot of other work has been done since this that refines on these ideas. But this is fairly straightforward and simple, so I think I'm just going to stick with this work. And the paper's available for everyone listening to this right now or watching this right now, so you can read it in all of its gory details. But I just want to go over the high-level bit here because I really think it kind of gets at this idea. So in particular, the paper that I'm talking about introduced an algorithm called MIMIC, which actually stands for something, though I forget what. And it really had a very simple structure to it. The basic idea was to directly model a probability distribution.
Probability distribution of what?
Well, I'll tell you. And, like I said, Michael, I will define exactly what this probability distribution is for you for a second, and hopefully you'll buy that it seems like a reasonable distribution to model. And given that you have this probability distribution that you're directly modeling, it, the goal is to do this sort of search through space, just like we did with all the rest of these algorithms, and to successfully refine the estimate of that distribution. And the idea is that if you can directly model this distribution and refine it over time, that will in fact convey structure.
Structure in particular of what we're learning about the search space while we're doing the search.
Exactly. And not just simply the structure of the search space, but the structure of the parts of the space that represent good points or points that are more optimal than others.
Yeah, that seems like a really useful thing.
So I'm just going to give you, again, this simple MIMIC algorithm that sort of captures these basic ideas because I think it's fairly simple and easy to understand while still getting at some of the underlying issues. But do keep in mind that there's been literally decades of work since then in the optimization space where people have really taken these kinds of ideas and refine them to sort of be much more mathematically precise. But this, I think, does get the idea across, and I happen to understand it, so I thought that I would share it with you. Seem fair?
Yeah, that sounds really exciting.
Excellent. Okay, so here's a probability distribution I'm going to define for you, Michael. You'll notice that it's a probability over our x's, and it's parameterized by theta. So theta is going to turn out to stand for threshold. Okay, got it? Mm-hmm. Okay, so here's the probability distribution. It is 1 over z sub theta for all values of x such that the fitness function is greater than or equal to theta.
Yeah.
And it's 0 otherwise. So do you understand that?
I think so. So I assume that z sub theta here is going to be some kind of normalization factor that accounts for the probability of landing or choosing an x in that space, in the space of high-scoring individuals above threshold.
That's exactly right. So another way of saying this is that this probability is uniform over all values of x whose fitness are above some threshold.
Yeah, so the image I have in my head is kind of like a mountain range, and if you put a slice through it, then everything that's kind of above that slice, we're going to sample uniformly from that collection.
That's right. And everything below it, we will simply ignore.
Doesn't happen. It doesn't get sampled from.
Exactly. Okay, so because you demanded it, Michael, here's a quiz.
All right.
So 2 questions in this quiz. The first question is, theta is some threshold, and so let's imagine the fitness function has to have some minimum value and some maximum value, okay?
Mm-hmm.
And let's call those theta sub min and theta sub max, respectively.
Mm-hmm.
And so I want you to describe in 1 or 2 words p sup theta min of x. That is the probability distribution where the threshold is its minimum value, and p sup theta max of x. That is the distribution where theta is at its maximum value. You got it?
So just to be clear, sort of the maximum meaningful and minimum meaningful values, because I can
Right.
imagine them, if it's just sort of way outside the range of the fitness function, then it's kind of trivial, I guess.
Right. Well, it is, but let's assume that theta min is the lowest value that the fitness function can take on, and theta max is the largest value that the fitness function can
Okay,
take
yeah, okay, that's how I was imagining it.
on. Okay. Good.
Okay, yeah, I'm good to go.
Okay. So go. Okay, Michael, you got an answer for me?
Yeah. This is the way I was thinking about it was essentially, well, for the theta min, wait, so we're maximizing, right?
Yes.
All right, so theta max then is going to be the largest value that f can return,
Yep.
which is actually the optimum of the function. So that probability distribution assigns a probability of, 1. If there's a unique optimum, it'll assign a probability of 1 to that single point.
That's exactly right. But you were getting at something else when you said if there's one optimum. What if there are multiple optima?
Then it's uniform over all of them.
Right. So it is the distribution that generates only optimal points. So it's the distribution over optima, which is just what you said. And we'd accept optimum point or anything that sort of captured this idea.
Okay.
Okay. What about theta sub min?
So if it's the minimum value that the function can achieve, then it ought to be the case that everything in the space of x's is part of that. So it should assign uniform probability to all points in the input space.
That's exactly right. So it is, in fact, simply the uniform distribution.
Nice.
Now, this is going to be pretty cool because in this slide right here, we basically have the mimic algorithm.
I'm not seeing it.
Well, I'm about to tell you. We are basically going to try to estimate this particular distribution, p sup theta of x. We're going to start out with p sup theta min of x, which is the uniform distribution. So we're going to sample uniformly from all of the points, and then somehow use those points to do better and better and better and better estimates until we get from uniform to a distribution over only the optimal points. And that's the basic idea.
So, okay, so and the first one being something that's really easy to sample from, because we're just sampling uniformly from the input space.
Right.
And the second being something that would be really useful to sample from, because if we could sample from the set of optima, it's really easy to find an optimum.
Exactly. So we'll start out here, and the goal is to start out here and then to end up here.
Gotcha.
And so let's actually write out an algorithm that does that.
Yeah, because that's not an algorithm, that's just a goal.
But many algorithms start out as goals. Okay, so Michael, here's some pseudocode that represents an algorithm of the sort I just described after the last quiz. So here's the basic idea. Just see if you can picture this. We're in the middle of this process. We have some theta at some time step t, and we're simply going to generate samples that are consistent with that distribution. So we're going to treat our probability distribution as not just something that gives us a probability, but something from which we can sample. So generate samples according to p sup theta sub t. Generate a bunch of those samples, and now that we have these samples, we're going to come up with a new theta, t plus 1, and that theta t plus 1 is going to be the best samples that we just generated. So let's say the top half. Now, you'll notice that this should actually remind you of something. Does it remind you of any of the other randomized algorithms that we've looked at so far?
Maybe a little bit like simulated annealing.
No.
Because it does, change the probability of going up. Where we're choosing things for a percentile. That's a lot like genetic algorithms.
Right. It's exactly like genetic algorithms, except instead of having this population that moves from one bit to the other, we generate samples that's like our population. So we generate a population here. We pick the most fit of that population by retaining only those that are the best ones. And all the stuff that you said before about, well, maybe you don't want to pick the best ones. Maybe you want to sample it according to a probability distribution proportional to the fitness. All those things you talked about before would apply here. But let's just stick to the simple case where you take the best ones. And now that we've got this new population, rather than using that population again, we estimate a new distribution that's consistent with those. And then we just lather, rinse, repeat until we come to some convergence.
Okay, so let me just make sure I'm following. First of all, when you say pea soup, you don't mean the food.
I do not, because I do not like pea soup.
And you don't mean soup meaning like the largest possible value of theta. Because when I was hearing pea soup theta, I kept thinking that you meant the best theta.
No, soup is short for superscript. Just
Superscript.
Like
All right.
people say p sub I, which means subscript.
Oh yeah. Okay. That makes sense.
Mm-hmm.
And okay, so now that that's now that that's clear, this notion of estimating a probability distribution, I guess that's where it feels really fuzzy to me. Because if you do the estimate as a kind of, I don't know, sort of particle filtery kind of thing, where you just keep instances, then it feels really a lot like the genetic algorithm.
Right. Except remember, one of the things that we cared about was structure. So this structure that we're maintaining, remember this complaint that I had that we weren't somehow keeping track of structure in a nice way,
Yeah.
is all going to be hidden inside how we represent these probability distributions. That is going to be the structure that moves from time step to time step rather than just the population of points moving from time step to time step. And I'll get into some details about that in the very next slide. I just want to make certain that you understand the high level bit here.
The high level bit.
And
Yeah, I mean, I'm not yet connecting it with theta in the sense of the previous slide.
So theta is our threshold, right? So basically we have some distribution. Now remember, what is p superscript theta? It is a probability distribution that is uniform over all points that have a fitness value that is greater than or equal to theta, right? So I have some distribution here. If I generate samples from that distribution, then what this means is I'm going to be generating all the points whose fitness is at least as good as theta. And then I'm going to take from those the set of points that are much higher than theta, hopefully, and use that to estimate a new distribution. And I'm just going to keep doing that. And what should happen is, since I'm constantly taking the best of those, is that theta over time will get higher and higher and higher, and I'll move from theta min over time to theta max. And when I get to theta max, I've converged and I'm done.
I see. So, all right, so the theta, right. So I guess I was confused because I didn't completely absorb the second line yet. So that we're updating the theta, and it's specifically going to be tracking I'm not sure what the nth percentile is.
So
is n the number of samples that we draw?
Oh, no, I'm sorry. Nth means, 50th percentile or 25th percentile or 75th percentile.
So, okay, so if you set that to be the median, which is the 50th percentile, then what we're doing is we're sampling, we're taking the top half of what's left, we're somehow refitting a distribution to that set of individuals that were drawn, and repeating in the sense that now the fitness of those individuals, the median should be higher because we're sampling from kind of a more fit collection.
Right. That's exactly right.
Okay.
So this should work, or at least it should match your intuition that would work, if there are sort of two things that are true. The first is that we can actually do this estimate.
Yeah, that's the part that scares me.
Sure. Well, given a finite set of data, can we estimate a probability distribution? So that's the first thing that sort of had better be true. And the second thing that needs to be true, and this is, I think, a bit more subtle, is that a probability distribution for p sub theta and a probability distribution for, say, p sub theta plus epsilon, that is a slightly higher value of theta, should be kind of close. So and what does that mean? What that means is that generating samples from p sub theta of t should give me samples from p sub theta of t plus 1. So I have to, that means that not only do I have to be able to estimate the distribution, I have to do a good enough job of estimating this distribution such that when I generate samples from it, I will also generate samples from the next distribution that I'm looking for.
Okay.
Okay, so if those things are true, then I hope you can at least sort of imagine that you would be able to move from the part of the space that's at theta min and eventually get to the part of the space at theta max.
Yeah, it seems like it should climb right up. Yeah, I agree with that. Assuming that you can represent these distributions in between. Again, the picture that I have in my head is like a bumpy mountainous landscape, and you put a slice through it. And in the beginning, yeah, right. So in the beginning, it's the whole space, and that should be easy to represent. At the end, it's a single point, and that's easy to represent. But in the middle, yeah, like that. But in the middle, it's this sort of crazy, there's a blob, then there's a space, then there's more blob. There's a little blob with a hole in it. So, like, that might be a much harder distribution to represent.
Right, and that's going to turn out to be an empirical question, but as I hope you'll see in a couple of slides, it tends to work out pretty well in practice.
Cool.
Okay, and by the way, when it doesn't work out well in practice, there's all these cute tricks that you can do to make it work out pretty well in practice, and we'll talk about that towards the end. Okay, Michael, so let me see if I can convince you that we have some way of actually estimating these distributions. So all I've written up here is the chain rule version of a joint probability distribution, okay? But just to be clear, what these subscripts mean here, every x that we have is made up of a set of features. So let's just say there's n of these features. And so really x is a vector. There's feature 1, there's feature 2, there's feature 3, ... all the way up to feature n. Okay?
Sure.
What I really want to know from my p sub theta, and I'm going to drop the thetas here for the purpose of just describing this generic distribution, is I want to say, well, the probability of me seeing all of the features, all of the features of some particular example is just the joint distribution over all of those features. Now, of course, we could just estimate this, but that's going to be hard. Why is it going to be hard? Because...
well, the first distribution is conditioned on a lot of things, so it's an exponential size conditional probability table.
Exactly. So this is exponential table, and if it's exponential table, then we need to have an enormous amount of data in order to estimate it well, and this is sort of the fundamental problem. But we have addressed this in earlier lessons, Michael.
In the inference lecture, maybe?
Yes, in the inference lecture, where we can try to estimate this incredibly painful joint distribution by making some assumptions about conditional independence. And in particular, I'm going to make one kind of assumption, and that is that we only care about what's called dependency trees. Okay, so what's a dependency tree, Michael? Do you remember?
No, I have absolutely no idea. I don't think I've ever heard of such a thing.
So a dependency tree is a special case of a Bayesian network where the network itself is a tree. That is, every node, every variable in the tree has exactly one parent.
I see. So sometimes in Bayesian networks they talk about polytrees. Polytrees just mean that if you ignore the direction of the edges, you have a tree. But you're actually talking about the edges have to go in a particular direction. Everybody's got one parent.
Right, exactly right. So you should see these as a directed graph, although I almost never draw them that way because it's sort of obvious by looking at it that this is the root of the tree. So all we have here now is a tree. Every node has one parent. And what does that mean? That means that every node, every random variable, depends on exactly one other random variable.
Yeah.
So we can rewrite this joint distribution here now as a product over each of the features depending upon only its parent.
I see. So the first capital pi there means product, and
Right.
the second lowercase pi there means parent.
Exactly. So when I compare this representation of a distribution, a dependency tree representation, versus the full joint, what nice properties do I get from doing it this way versus doing it that way?
Well, I guess the main positive is that you're only ever conditioned on, it's got to be at most one, right? Not exactly one.
Right, in most ones. So in fact, you picked up on a nice notational thing here. The parent of the tree, the root of the tree, doesn't actually have a parent. So just assume that in this case, pi returns itself or something, and so it's the unconditional distribution. And that could happen at any time.
Gotcha. All right. Yeah, and so like if nobody has any parents, then that's the same as naive Bayes. But here it can have at most one parent. No?
Naive Bayes has one, exactly. Everyone has one parent, and it's exactly the same one.
Oh, right. Good point.
So if everyone has no parents, then you're saying that all of the features are, in fact, independent of one another.
Gotcha. Okay, all right. But that's not what you asked. You asked comparing that probability distribution to the full joint. The main thing is that no one's ever conditioned on more than one other feature, and therefore the conditional probability tables stay very, very small.
Right. In fact, how small do they stay?
Well, it depends how big this are there binary features that we're talking about?
Yeah, let's say they're binary.
So then it's like it's two numbers, right? It's like your probability when your parent is true and your probability when your parent is false.
Well, that's each table, but what about representing the entire thing?
So it's going to be linear in the size of the number of variables or features.
Right, and the amount of data that you need is going to be fundamentally. In order to get this tree, it's going to turn out that you only need to keep track of a quadratic set of numbers, quadratic in the number of features.
We're not going to be given that tree. We're going to have to figure it out.
Well, remember, one of the steps of the algorithm is you have to estimate the distribution. So we're going to have to figure out, of all the trees that I might have, what's the best tree.
Yeah, that doesn't exactly follow from the algorithm sketch, because you could also say, well, then you need to figure out that a tree is the right thing at all instead of something else like a box.
Oh, that's fair. But what we're going to do is we're just going to assume that we're going to do dependency trees. Now, why are we doing this? We're actually doing this for a couple of reasons, Michael. Your point's your point's well taken. Dependency trees have this nice feature that they actually let you represent relationships. The point is that you're actually able to represent relationships between variables, which in this case are sort of features in our space, but you don't have to worry about too many of them. And the only question here then is, how many relationships do you want? Which of all the possible relationships you could have where you only are related to one other thing do you want to have? Well, in some sense, a dependency tree, since you can depend on at most only one other thing, is the simplest set of relationships you can keep track of. The next simplest would be, as you point out, not having any parents at all, in which case you would be estimating simply this.
Yeah, I wouldn't say that's the next simplest. That's even simpler, but it doesn't allow any of the interrelationships, any of the covariance, essentially, information to be captured.
No, that's fair. That's a fair point. So we could have started with something like this, except here you are forced to ignore all relationships because you're treating everything as independent, and we don't believe that things are independent, or at least we think there's a possibility there's some dependence. And so by allowing at most that you're connected to one other parent, that's sort of the least committed to the idea you could still be while still allowing you to capture these relationships. So that's the basic idea. Now, I want to be strict here that the mimic algorithm, or just this whole notion of representing probability distributions, does not depend upon dependency trees. We're going to use dependency trees here because you have to make some decision about how to represent the probability distributions, and this is kind of the easiest thing to do that still allows you to capture relationships.
I buy that.
Okay, and one other thing worth noting is, I hope you'll see this in a couple of slides if you don't see it immediately, is that at the very least this will allow us to capture the same kind of relationships that we get from crossover in genetic algorithms.
Huh.
And that was a bit of the inspiration for this, that crossover is representing structure, in this case structure that's measured by locality, and this is kind of a general form of that.
So you're saying if there is some locality, then however we're going to learn the dependency tree from the samples is going to be able to capture that, and therefore it will kind of wrap its head around the same kind of information that crossover is exploiting.
That's exactly right. And in fact, as we'll see in one of the examples that I'll give you in a moment, that it can do better than that because it doesn't actually require locality the way that crossover does. There's one other thing that's worth mentioning here about this distribution and why it's nice. It captures relationships. But the second thing is something that you sort of alluded to earlier, is that it's very easy to sample from. Right? So given a dependency tree where each one of these features, each one of these nodes represents a feature, it is very simple, very easy to generate samples consistent with it. Right? You just start at the root, generate a sample, unconditional sample according to whatever the distribution is, and then you go through the parents and you do the same thing. So it's exactly a topological sort, and in trees, topological sorting is very easy, and this is in fact linear in the number of features.
Right, I get that, and it is exactly an instance of what we talked about when we did Bayesian inference. The thing that is new is how do we figure out a dependency tree from the sample?
Exactly, that's what we're going to do next, and that's going to involve math. Okay, Michael, so what I'm going to do is I'm going to step through how you find dependency trees, and just stop me if it doesn't make any sense, okay?
Sure.
But hopefully it's fairly straightforward, at least if you understand information theory. And again, I want to stress that although we're gonna spend some time doing this, this is just one example of ways that you could represent a probability distribution. It's just going to turn out that this one's particularly easy and powerful, okay?
Exciting.
Okay, so the first thing we have to remember, Michael, is that we have some true probability distribution, which I'm just going to write as P, that we're trying to do. That's our P sup theta in this case. But the general question of how you represent a dependency tree doesn't depend on theta or anything else. There's just some underlying distribution we care about. Let's call that P, okay? And we're going to estimate it with another distribution, which I'm going to represent as P hat because, for approximation, that's going to depend upon that parent function that we defined before. Okay?
All right.
So somehow you sound skeptical, Michael.
Well, because I saw that you wrote those train tracks.
And you figure they must mean something?
Well, I know they mean something. It's an information theory thing, but I'm not going to remember what it is. You're gonna say something like KL divergence or something.
That's exactly right. So somehow we want to not just find a P hat sub theta, that is a dependency tree that represents the underlying distribution, but we want to find the best one. And so best one here sort of means closest one or most similar, or the one that would generate the points in the best possible way. And it turns out, for those of you who remember information theory, that there's actually a particular measure for that, and it's called the KL divergence. You remember what the KL divergence stands for, Michael?
Kohlbach-Leibler.
That's right. And it has a particular form, and in this case, let's assume non-continuous variables. It has basically this form. And that's basically a measure of the divergence, that's what the D stands for, the divergence between the underlying distribution P that we care about and some other candidate distribution P hat that we're trying to get as close as possible. So if these are the same distributions, if P hat and P are the same distribution, the Kohlberg-Leibler divergence is equal to 0. And as they differ or as they diverge, this number gets larger and larger. Now, it turns out that these numbers are unitless. They don't obey the triangle inequality. This is not a distance. This is truly a divergence. But if we can get this number to be minimized, then we know that we have found a distribution P hat that is as close as we can get to P. Okay? And we have a whole unit that Pushkar will do to remind everybody about information theory and where this comes from. But basically, this is the right way to define similarity between probability distributions. You just have to kind of take that on faith.
Okay. Well, I'll pause this and go back and listen to Pushkar's lecture, and then I'll be ready for you.
Okay, beautiful. Okay, so what we really want to do is we want to minimize the Kohlberg-Leibler divergence, that is, minimize the difference between the distribution that we're going to estimate with the dependency tree and the true underlying distribution. And just by doing some algebra, you end up getting down to what looks like a fairly simple function. So, Michael, if you were paying close attention to the algebra, you will realize that, well, P log P, now that you've come back from Pushkar's lecture, is just entropy. So, or it's minus the entropy. And so I can rewrite this as simply minus the entropy of the underlying distribution plus the sum of the conditional entropies for each of the xi's given its parent, which has some sort of intuitive niceness to it. But whatever. This is what you end up with just by doing the substitution. P log P gives you minus entropy of P minus P log P hat, which gives you the conditional entropy according to the parent function pi. Okay?
Good.
Well, in the end, all we care about is finding the best pi, so this term doesn't matter at all, and so we end up with a kind of cost function that we would like to minimize, which I'm going to call here j, which depends upon pi, which is just the sum of all the conditional entropies. Basically, the best tree that we can find will be the one that minimizes all of the entropy for each of the features given its parents. Does that make any intuitive sense to you?
Yeah, I think so. Because we want to choose parents that are going to give us a lot of information about the values of the corresponding features.
Right. So in order for this to be minimized, you would have to have picked a parent that tells you a lot about yourself, right? Because entropy is information, entropy is randomness. And if I pick a really good parent, then knowing something about the parent tells me something about me, and my entropy will be low. So if I can find a set of parents for each of my features such that I get the most out of knowing the value of those parents, then I will have the lowest sort of sum of entropies, conditional entropies. You with me?
Yeah.
Okay. Now, this is very nice, and you would think we'd be done, except it's not entirely clear how you would go about computing this. Actually, I know how you would go about computing it, and let me tell you, it's excruciatingly painful. But it turns out that there's a cute little trick that you can do to make it less excruciatingly painful. And what I'm going to do is I'm going to define a slightly different version of this function. and I'm going to call it j hat. So as I said before, we want to minimize this particular cost function j, which we get directly from the Kolbe-Leibler divergence. And so all I've done is define a new function j prime where I've added this term, just minus the sum of all of the unconditional entropies of each of the features. Now I'm able to do this because nothing in this depends upon pi, and so it doesn't actually change the proper pi. Does that make sense?
Yeah, except I keep thinking about pi.
Pi. Oh, I'm sorry, you got me distracted. Okay, but do you see how minimizing this versus minimizing this should give me the same pi?
I do. I mean, it's sort of like adding a constant. If you've got a max, it doesn't change which element gives you the max.
Right. But by adding this term, I've actually come up with something kind of cute. What is this expression, Michael? Do you know?
It looks kind of familiar from information theory. Is that cross entropy?
No, though sort of, but no.
Is it mutual information?
It is, in fact, mutual information. In fact, it's the negative of mutual information. So minimizing this expression is the same thing as maximizing mutual information. Now, I went through this for a couple of reasons, Michael. One is I think it's easier to kind of see what mutual information is, but also because this is going to induce a very simple algorithm, which I'll show you in a second, for figuring out how to find a dependency tree. And the trick here is to realize that conditional entropies are directional, right?
Wait, so conditional entropies is that's the quantity that we started up top with the hx. Okay.
Right. So this is directional, right? Xi depends upon this.
Yep.
And if I were to do h of pi given xi, I would be getting a completely different number. Mutual information, on the other hand, is bidirectional.
Interesting.
And it's going to turn out to be easier to think about. But before we do that, let's just make certain that this makes sense. So we wanted to minimize the Kolbe-Leibler divergence because that's what Shannon told us to do. We work it all out, and it turns out that we really want to minimize a kind of cost function, another way of rewriting this, of conditional entropies. We threw this little trick in, which just allowed us to turn those conditional entropies into mutual information. And what this basically says is that to find the best pi, the best parents, the best dependency tree, means you should maximize the mutual information between every feature and its parent.
Nice.
Right, and that sort of makes sense, right? I want to be associated with the parent that gives the most information about me.
Charles, I have a question.
Yes.
I'm just a little bit confused. The XIs, what are they? Where's that bound?
Oh, by the summation.
What summation?
You know, the summation that's always been there the entire time I've been talking.
Oh, I'm sorry I missed that.
I don't know how you missed it, man. It's right there.
Yeah, I mean, you didn't actually put the index in the summation, so I was confused.
My fault. Right. So just to be clear for anyone who noticed that, the Kolbe-Leibler divergence is a summation over all possible variables in the distribution. And so all we've done here is carry that all the way through. And so these two steps here in particular, this new cost function that we're trying to minimize is a sum over the negative mutual information between every variable, every feature, and its parents. And that's the same thing as trying to maximize the mutual information, the sum of the mutual informations between every feature and its parents.
Interesting.
Right. And again, I think that makes a lot of sense, right? You basically, the best dependency tree is the one that captures dependencies the best.
I see. All right. That's cool. All right. So now we need to figure out how to do that optimization. Exactly
right. And it turns out it's gloriously easy. All right, Michael, so see if you can tell me where we're going here. So just as a reminder, I've erased a bunch of stuff so I can make some room. We're trying to maximize this cost function j prime sub pi, which is basically the sum of the mutual information between every single feature and its parents. And I want to point out that that actually induces a graph, in fact, a fully connected graph. So here I've drawn a bunch of nodes as part of a graph and all the edges between them. Each one of these nodes is going to represent a feature, an x of I, and what's going to go on the edges is going to be the mutual information between them. So I now have a fully connected graph, which has the mutual information between each pair of nodes, all n-squared edges, and I want to find a subgraph of this graph, in particular a tree, that maximizes these sums. So, any ideas how I do that, Michael? First off, does that make sense what I just said?
Yeah. I mean, it's very interesting, right? So we're trying to pick each time we pick an edge, it's actually saying that what we're going to care about the relationship between this pair of variables, and we're only allowing edges. We're not allowing because they that involves two nodes. We're not getting sets of 3 or 5 or however many nodes larger than that. And so what we want is we want to be considering a subset of edges that form a tree that has the highest total information content.
That's
And
exactly
that's
right.
and that's a minimum spanning tree.
Well, not quite.
That's a maximum spanning tree.
That's exactly right. It turns out that finding the tree consistent with this graph, such that this is true, is in fact the same thing as finding the maximum spanning tree, which we all vaguely remember from our algorithms class.
So you said it was terribly painful, but it's actually not. This
No, I
is
said it's terribly easily painful. So that's really neat. We turned the problem of finding the best distribution, and in particular the best dependency tree, independent of the true underlying distribution, I want to point out, into a problem of a well-known, well-understood computer science problem of finding the maximum spanning tree. If we find the maximum spanning tree, then we have found the best dependency tree.
So to be honest, I don't remember maximum spanning tree. Minimum spanning tree, can we just solve a maximum spanning tree problem by, I don't know, negating the edges or
Yes.
adding? Okay.
That's exactly right. So everywhere in there where you pick a max, you pick a min, or you just label them with the negative of the mutual information, and it's the same thing. I think that this particular form of writing it as a maximum mutual information is easier to think about.
Okay.
And what you'll do when you find the maximum spanning tree is you'll end up with, in fact, some tree, and you're done.
Well, so now you need to tell me, because the structure was a directed structure. So can we then pick any node and call it the root and then do a depth first traversal or something?
Absolutely. So first off, I want to point out there's two different algorithms that you could use. Do you remember the two algorithms you could use to find the maximum spanning tree? Or the two famous ones anyway?
I'm going to go with Prim and Kruskal, but I know there's others.
No, those are the two that they teach you in algorithms class. And it turns out for this particular one, you want to use prim because prim is...
It's proper.
It is proper, prim and proper. Prim is the proper algorithm to use whenever you have a strongly connected graph. It just happens to be faster.
You mean densely connected graph?
What did I say?
Strongly.
Okay, densely connected. Right, a densely connected graph. And by the way, this is a fully connected graph, which is about as dense a connected graph as you can get. So Prim's algorithm runs in time quadratic, or polynomial anyway, in the number of edges. And so it's actually fairly efficient as things go, because as we know, in theory, if it's polynomial, it might as well be free. And there you go. So use Prim's algorithm, you find the maximum spanning tree, and you are done.
All right, I'm going to need reminding where this is all plugging in.
Okay,
Because
that's exactly what I was going to
do.
do.
Cool diversion, but...
Right, so it is actually worth pointing out that this was a bit of a diversion that we had to do. Let's go back to the original algorithm that we had and just point out what we would be doing here. Okay, Michael, so let me take you back to the pseudocode that we had for Mimic and see if we can plug in some of the stuff that we just talked about, just as a way of refreshing. So as you recall, the goal is to generate samples from some p sup theta sub t of x. So in this case, we're just going to estimate that by finding the best dependency tree we can, that is the best pi function. Okay, so we're going to be starting with some dependency tree, and we're going to generate samples from that, and we know how to generate samples from that. Given a dependency tree, like say this, we simply start at a node, generate according to its unconditional distribution, and then generate samples from each according to its conditional distribution given its parent. So first we generate a sample from here, then we generate one from here, then from here, then from here, and then from here. Now, where do we get these conditional probability tables, Michael?
That's a good question. I think it's pretty direct from the mutual information.
Exactly. In order to compute the mutual information, that is, in order to compute the entropies, we have to know the probabilities. So we generate all of these samples, and that tells us now for every single feature x of I, how often that was, say, taking on a value of 1 or taking on a value for 0, if we assume everything's binary. So that means we have unconditional probability distributions, or at least estimates of unconditional probability distributions for every single one of our features. Yes?
Yep.
And at the same time, because we have these samples, we know for every pair of features the probability that one took on a value given a value for the other. So we already have the conditional probability tables for each of those as well. So just the act of generating these samples and building that mutual information graph gives us all the conditional and unconditional probability tables that we need. And so given that, we can generate samples in time linear in the number of features, and we're done. So this part is easy. By the way, you asked me a question before. I just want to make it clear that we come back with an undirected graph. And you can pick any single node as the root, and that will induce a specific directed tree. And it actually just follows from the chain rule. And I'll leave that as an exercise to the viewer. But there you go. So now we know how to generate samples from some tree that we have. We generate a bunch of these samples. We find the best ones, retaining only those samples. And now we know how to estimate the next one by simply doing the maximum spanning tree over all the mutual information. And then we just repeat, and we keep doing that. And there you go. A particular version of Mimic with dependency trees. Got it?
Cool.
Right. So again, just to really drive this point home, you don't have to use dependency trees. You can use unconditional probability distributions, which are also very easy to sample from and very easy to estimate. You could come up with more complicated things if you wanted to, try to find the best Bayesian network. You can do all of these other kinds of things, and that'll work just fine. Dependency trees, though, are very powerful because they do allow you to capture these relationships. That is to say, they give you a probability distribution that has structure that we were looking for while not having to pay an exponential cost for doing the estimation. Okay, so we're going to have a quick quiz. Michael insists on having one because Michael likes that sort of thing, and I like Michael, so I'm going to go with him and give you a quick quiz to see if you follow along with what we've talked about. Now, this quiz is less about the details of Mimic itself than it is about the probability distribution. So I've been harping on this idea that Mimic doesn't care about your probability distribution. You should just pick the best one. So we want to make certain that you get that by giving you 3 problems and 3 probability distributions you might use and see if you can tell us which one goes with which. Okay? So here are the 3 problems. The first problem is your fitness function is to maximize the number of ones. So the first thing you need to see is that we're going to assume in all of these cases that our input values x are binary strings of length n. Okay, so 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 1, 1, 1, 1, 0, 0, 1, 1, 1, whatever. There's going to be a string of ones or zeros, so they're binary digits. And the first problem, we want to maximize the number of ones that appear in that sample. Do you get that, Michael?
Yeah, I mean that's going to be maximized by just making everything a 1, right?
That's right. That's right.
Okay, but we want to think about Mimic finding that.
Right, because you don't know that that's the true underlying fitness function. That just happens to be what it is.
I see. Okay, good.
Okay. So in the second problem, we want you to maximize the number of alternations between bits. So 0, 1, 0, 1, 0, 1, 0, 1 is better than all ones. Much better than all ones, in fact, because the fitness you would get for maximize alternations between 0, 1, 0, 1, 0, 1 is, in fact, n minus 1, which is the largest that could be. But if you had all the digits being the same, your fitness would be 0. You see that, Michael?
N minus 1. Oh, I see. N minus 1 because it every time it switches.
Right.
Got it.
So what would maximize the number of alterations in, say, a 5-digit string?
Like 0, 1, 0, 1, 0.
Or?
The complement of that, 1, 0, 1, 0, 1.
Right, so 2 values both act as maxima here. Okay, the third problem is you want to minimize 2 color errors in a graph. Now that one's a little bit harder to describe, so I'm going to draw a little graph for you. So the 2 color problem, you might remember, is given a graph with some edges, like say this graph here, you want to assign a color to each node such that every node has a different color than its neighbor. Okay, so we assume there's only 2 colors here, 1 and 0. So let's say I assign this the color value of 1, this the color value of 0, this the color value of 0, this the color value of 1, and this the color value of 1. So how many errors are there, Michael?
Wait, we should be trying to maximize. But okay, so I guess not. So minimize 2 color errors. So an error would, in this case, would be an edge that has the same color on both ends, and I see one of those, the bottom sort of rightish.
Right. So here these do not match, so that's good. These do not match. These do not match. But these 2 match, even though that one doesn't. So there's exactly 1 error. So in these first 2 examples, we're trying to maximize a fitness. Here we're trying to minimize a cost just to make things slightly more difficult for you. If we removed this edge here, then you'll notice that this has no mismatches whatsoever, and this would be an optimum.
Got it.
Okay, so we need to figure this out. Okay, so there we go. We want you to maximize the number of ones in your string, or maximize the alternations by adjacent bits, or to minimize the number of 2 color errors in a graph. All right, those are the 3 problems. Now here are the 3 distributions. The first distribution, these are in alphabetical order, is a chain. So a chain would be, in kind of Bayesian network speak, A chain would be a graph like this, where basically every feature depends upon its previous neighbor. So in a 4-bit string, I'm saying that the first bit depends on nothing, the second bit depends on the value of the first bit, the third bit depends on the value of the second bit, and the fourth bit depends on the value of the third bit. So the way you would generate samples is you would generate a sample from here, and then generate a sample on here dependent upon this value. Given that value, you generate a sample here, given that value, and you generate a sample here, given that value. Got it, Michael?
I think so. So, and we're imagining that the ordering is given, so we know which ones depend on which.
Right. So in fact, it's not just a chain; it's a specific chain.
And is it the same chain as, say, the ordering of the bits?
Yes. In this particular case, it's the same chain as the ordering of the bits. So I'm going to call this that chain.
All right.
Okay. The second one is what we've been talking about all along. It's a dependency tree. Unlike in the case with this chain here, where I'm giving you a specific chain. This is the first bit, the second bit, the third bit, the fourth bit, and so on to the nth bit. I don't know which dependency tree is here. You'd have to find it. But there's some dependency tree I want you to represent. And the third one is the easiest one to think about, and that's where everything is independent of everything else. So if I were to draw that, it would be a bunch of nodes with no edges between them, directed or otherwise. And so the joint probability across all your features is just the product of the unconditional probabilities. Sort of the simplest probability distribution you can have. Okay, you got that, Michael?
Yeah, so, okay, if I'm understanding correctly, each of these is actually representable by a dependency tree.
Yeah, each one is actually.
So then why would anyone be better than any other one?
I don't know, Michael. You tell me.
I guess in the case of, well, it could be, you could think of it maybe in terms of the number of parameters that need to be estimated. So in the independent case, since we know that it's independent, or at least we're imagining it's independent, we just have to estimate one probability per node, which is like n.
Yep.
In the chain case, we have a conditional probability per node, so it's like 2n parameters.
Yep.
And in the dependency tree case, it's, I think what you were saying is that we're estimating kind of n squared parameters and then pulling the tree out of that.
Exactly. Now, of course, like you point out, Michael, each of a chain is a dependency tree. Independents are a dependency tree. And a dependency tree is, surprisingly enough, a dependency tree. But these numbers of parameters do matter because although a dependency tree can represent an independent set of variables, the way you're going to discover that they're independent is you're going to need a lot of data to estimate those n squared parameters in order to realize that the conditional probability tables effectively don't mean anything. So it would be very easy for a dependency tree to overfit in the case where all the variables or all the features are actually independent.
Okay.
Okay. All right. So you got it?
All right. No, not one more question.
Yes.
Well, other than what, I need to fill the boxes in with the numbers 1, 2, or 3, right?
Yep. Of
and
the algorithm that they're best for, or the
each one of
problem.
them is,
they're best for.
Got it. And each one is used exactly once.
Yes.
Okay. And then finally, just to kind of make sure that I'm wrapped my head around why we're doing probability distributions at all. So in the context of Mimic, we need some way of capturing I guess the space of answers that do at least a certain level. They do at least this well in terms of the fitness. So I guess I feel a little thrown off because we're not trying to represent the fitness functions, right? You're not telling me which dependency structure should I be using to represent this fitness function.
Right. Instead, I'm asking you to figure out which distribution will represent the optima, the structure between the optimal values.
Okay. All right. I'm not sure I 100% get it, but I think I get it enough to answer this quiz.
Excellent. Okay, so go. Okay, Michael.
Okay, so problem 1, where you're maximizing the number of ones, to represent the optima here, or the influence of any given bit on the fitness value, they're all independent. They all just contribute whatever they contribute. And so I don't see any reason to capture other dependencies. Local information is enough. Is that enough to say that the answer, that the 1 goes in the last box for independence?
That's correct.
But I guess what I don't quite understand is in the case of so we want to know what's the probability. Yeah, it's a funny thing we're representing, right? So
Yeah.
So if like the third position, we're saying, well, what's the probability that if this is a 1, that we're going to be above a certain value? And what's the probability if it's a 0, we're going to be above a certain value? And that doesn't really exactly capture the way the fitness function works. But I guess because we're drawing the rest of the things at random, the rest of the values at random.
Mm-hmm. Yeah, we are.
So is that where the meaning comes from then?
Yeah, think about it this way. Remember, the probability distribution that we care about, P sub theta, is basically uniform for all x's such that the fitness value is greater than or equal to theta. So imagine we start out with theta equal to 0, let's say, which is the lowest value that you could get. Well, then what's the probability of bit 1 being a 1?
Okay.
For all values greater than theta, well, it's 1/2.
Okay.
Because every single value is okay. And so in order to get a uniform distribution across n bits, I can sample each bit independently uniformly, and that'll give me an overall uniform distribution. Agreed?
I do agree with that, yeah.
Okay. Now at the very, very end, when I have all ones as the maximum value, that's also easy to represent because what's the probability of bit 1 being 1 for the optimal value?
1.
Yes, and the probability of bit 2 is?
1.
And the probability of bit 3?
No, 1.
Exactly. And they're all can be independently represented. So we can definitely represent the minimum theta value.
Extremes, yeah.
Yes, and we can represent the maximum. The question here is, or at least in terms of, your likelihood of finding the answer, the question here is, can this distribution represent values of theta in between? So imagine theta was, let's say I had 4 bits here, we're doing here, and let's imagine theta was 2.
Good.
Now, notice that when theta is 2, it's not just the number of points that will give you exactly 2. It's the ones that will give you at least 2. 2
right.
and 3 and 4. So how many different ways are there to get 4? Well, there's only one way to get a value of 4, and that is all ones. How many different ways can you do 3? Well, there's 4 ways to get 3. You basically have to choose the one that you give it a 0, right? And each one of those bits, each one of these values will be a 1 3/4 of the time. And how many different ways can you get 2? Well, it's n choose 2, which is something.
6.
6. So you can actually write all of those out and count the number of times that each one is a 1. And those are all your samples, and you just simply estimate it. And you'll end up with a uniform distribution, which will be consistent with the examples that I just sampled from, but will probably not exactly capture P sub theta, because it will sometimes be able to generate, with probability not greater than 0, say a value of all zeros.
Yes. Okay, good. That was what I was concerned about. And so it is just an approximation even in this simple case.
Right. And that's actually pretty interesting, right? So yeah, we know that the extreme values can be represented by an independent distribution, but it's not clear that all the values in between can be represented by such a simple distribution. But that's always going to be the case. What you want is a distribution that will definitely capture the optimum or optima, and gives you a good chance of generating samples that get you closer to the optimum along the way. So even though in the case before where theta is 2, we might still generate examples where you get a fitness of 0 or 1. You have a high probability, if you generate enough samples, of actually getting values of theta greater than 2, 3, or 4 even.
Got it.
Okay.
All right. So given that, I think I can do the next 2 without too much more difficulty. So for number 2, problem 2, maximize the number of alternations. We pointed out that it's really important to know who what your neighbor is, because you want to be a different value than your neighbor. And the chain gives you exactly that information without anything extra.
Right.
So I would put the 2 in the first box.
Yep.
And finally, well, there's only one box left, so I'd put the 3 in the middle box. But I guess the interesting thing to look at here is that it is surprisingly appropriate, right? So that the coloring problem, it is specifically saying, well, my value depends on, what's a good value for me depends on, I guess, several of my neighbors, not just one.
Right.
But I feel like you could capture a lot of the necessary information by finding a good dependency tree.
Right. And it turns out that in practice, as our readers and listeners will see from one of the resources that we're making available to them, that in practice, Mimic does very well on problems like this. Even where you have really complicated graph structures, it tends to do much better than a lot of the other randomized optimization problems. And that's because what we've got here in this graph is structure. And what Mimic is trying to represent is, in fact, structure. In fact, in all of these cases, well, except for the first case, there's not a single answer often. There are possible many answers, but the answers all have in common their relationship to some underlying structure. So in the maximizing alternations case, you have 0, 1, 0, 1, 0, 1, or 1, 0, 1, 0, 1, 0. These are two completely different values. In fact, as you pointed out when I asked you this earlier, they're complementary. But each one has a very simple structure, which is every bit is different from its neighbor, actually both of its neighbors. Every bit is different from its neighbors. And that doesn't matter what their values are. Given the value of one of them, it actually completely determines the value of everything else, right? And so Mimic doesn't get lost trying to bounce back and forth between this possible maximum and this possible maximum. Instead, it represents both of them at the same time because the only thing that matters is the relationships. So in fact, that gets us to the last bit of things I wanted to talk about, which are sort of practical features of Mimic and what we kind of learn by thinking this way. Okay, so here's some practical matters, Michael. I mentioned one of them before, and that is that Mimic does well with structure. When the optimal values that you care about depend only on the structure as opposed to specific values, Mimic tends to do pretty well. By contrast, randomized hill climbing, genetic algorithms, these other things that we looked at before can sometimes get confused by two different values that are both optima but look very different from one another, where it's the structure that matters and not the actual values. So the chain example before, where you had alternating values, is one of those cases where it's easy for randomized algorithms that only look for point values to get confused because they're basically being drawn in multiple directions at once. The quiz also brought up another point which is worth mentioning here with Mimic and with anything that tries to do this kind of search through probability space, is that it's an issue of representing everything. That is, it's not enough just to be able to represent a probability distribution of the optima. You really want to be able to represent everything in between. As you move through probability space towards your answer, this is the universal symbol for moving through probability space. You don't just want to represent here at the end and here at the beginning, which is pretty easy because it's a uniform distribution. But can you represent this point? Can you represent this point? And if you can't, are you going to end up getting stuck? And it actually turns out that Mimic can get stuck in local optima, though it typically does not, in part because you get randomized restarts for free.
I see.
But the problem of local optima is still a problem of local optima. Now, when I say something like you get randomized restarts for free, I'm actually cheating a little bit and hiding something which is a little bit more important, which is that what you really get for free is probability theory. So there's literally hundreds of years of work on how to think about representing probability distributions and what you can do with them. And there are terms like importance sampling and rejection sampling and all these kinds of tools that we have for representing probability distributions that you can actually inherit with something like Mimic for dealing with these painful cases where you might not be able to represent distributions. But the single most important thing to me about Mimic, or what to get out of here, is that representing structure does matter, but you pay a price. And that price basically boils down to time. So the question we might ask ourselves is, what is the sort of practical time complexity of Mimic? And it really boils down to something very simple. Let me just share with you a fact, Michael. Okay? I have run this algorithm on many, many, many examples, and I've compared it to simulated annealing, I've compared it to genetic algorithms, I've compared it to randomized hill climbing, and it works pretty well for the sorts of examples I've come up with. And here's a little fact that I just want to give you. Mimic tends to run orders of magnitude fewer iterations. And I'm not exaggerating here. I mean that if I run simulated annealing, it might take 100,000 iterations for something like simulated annealing, but for Mimic, it might take only 100. And this is consistently true. So it turns out that that's not good enough. It turns out that the fact that Mimic can do something in 3, 4, 5, 6, 7 orders of magnitude fewer iterations isn't an argument for always using it. Can you imagine why not?
Because it might give a worse answer?
Well, in practice, it doesn't. So these are cases where both simulated annealing and Mimic, or randomized hill climbing, or genetic algorithms actually eventually do find the answer. Mimic just finds it in orders of magnitude fewer iterations.
But you're counting iterations. You didn't control for the fact that different algorithms can take different times for a single iteration.
That's exactly right. So what do you think, if I were to compare simulated annealing to Mimic, which do you think takes more time for any given iteration?
Well, simulated annealing just does this little tiny step, right? It computes a bunch of neighbors and then does a probability comparison and then takes a step. Mimic is drawing this sample, estimating a bunch of parameters, then I guess the other way around. It's drawing from a distribution, it's computing which things are, say, above the median performance, and then it's re-estimating a new distribution, and then that's the end of the iteration. Depending on how many samples it takes to do that, it could take a very long time, and in particular, it's going to always be a lot more samples than what simulated annealing is doing.
Almost certainly. So when would you think that Mimic would still be worth using in a case like that, where we know that we can get to the answer, but simulated annealing will take orders of magnitude more iterations, Mimic will take fewer iterations? So when would it still be worth it to take the one with fewer iterations, even though each iteration is expensive? Prim's algorithm, quadratic this, that, and the other.
Oh, yeah, I forgot about that part.
Here, let me put it to you this way, Michael. What is Mimic giving you for all of that work that it's doing in building dependency trees and running Prim's algorithm and finding maximum spanning trees?
I'm going to say structure because that's the word that you've been using repeatedly.
You get structure. And another way of thinking about structure in this case is you're getting information. You get a lot more information because you get structure. You get a lot more information per iteration as well. So that's the price you're paying. You're getting more information every single time you do an iteration at the cost of building these maximum spanning trees or whatever it is you're doing in estimating your probability distribution. So why would it be worth it to do that? What's the other source of expense?
Well, all right, so there's all this computation within an iteration, but what it's trying to do is trying to find inputs that have high scores, and so you do have to compute the scores for all those inputs. So the fitness calculation is really important.
Right. So Mimic tends to work really well when the cost of evaluating your fitness function is high. So it's really important that I only have to take 100 iterations if every single time I look at a fitness function and try to compute it for some particular X, I pay some huge cost in time.
Well, have you told us how many function evaluations there are in an iteration? Because it seems like it could be a lot in Mimic.
Well, you get one basically for every sample you generate.
Yeah, so I guess you can compare iterations, but you can also compare samples.
Right. So that would depend upon how many samples you feel like you need to generate. And of course, you can be very clever because remember, theta will generate a bunch of samples for theta plus 1. So if you keep track of the values you've seen before, you don't have to recompute them. So it's actually pretty hard to know exactly what that's going to be. But let's imagine that at every iteration, you generate 100 samples. So at most, you're going to have to evaluate f of x 100 times. So Mimic is still a win over something else if the number of iterations that it takes is more than 100 times fewer.
Wow.
Right?
Yeah.
So can you think of fitness functions, real fitness functions that might actually be expensive to compute?
Well, yeah, sure. I mean, a lot of the stuff that is important is like that. So if you're trying to design a rocket ship or something like that, a fitness evaluation is doing a detailed simulation of how it performs, and that could be a very costly thing.
Right. Actually, that's a good example because Mimic has been used for things like antenna design. It's been used for things like designing exactly where you would put a rocket in order to minimize fuel costs, sending it to the moon. These sorts of things where the cost really is in evaluating some particular configuration where you have to run a simulation or you have to compute a huge number of values of equations and so on and so forth in order to figure out the answer. Another case where it comes up a lot is where your evaluation function, your fitness function, involves human beings.
Oh, interesting. Yeah.
Where you generate something and you ask a human, how does this look? Or does this do what you want it to do? Because humans, it turns out, are really slow.
Yeah, they're not measured in megaflops.
That's right. So you end up with cases where fitness functions are expensive. Something like this becomes a big win. And that's a general point to make, though, that when you're looking at all of these different algorithms, these different models for everything that we've been doing, both for unsupervised learning and earlier for supervised learning, a lot of times your trade-off is not just in terms of whether you're going to overfit or not. It's whether it's worth the price you need to pay in terms of either space or time complexity to go with one model versus the other. We've been talking about it in terms of sample complexity, but there's still time complexity and space complexity to worry about.
Cool. I get it.
Okay, cool. So normally what we would do next is we would say, what have we learned? But I actually kind of think we just did
that. Indeed.
So in fact, let me do something about that. So Michael, what have we learned?
That.
I think you're right. Okay. Well, Michael, I was happy to be able to share some of this with you and to remind myself of something I did 20 years ago.
And it answered the concern that you had, so it fit into the overall structure.
Excellent. Oh, it fit into the structure. Well done, Michael.
Oh, I see what I did there.
Yeah, very well done. Well, I will talk to you later, Michael. Thank you so much for listening.
Sure, thanks.
Bye.